full day. This is the toughest day of the week, you know. It's been very light so far. However, today we have several lectures. They're intense lectures, a lot of computer modeling, and we also have in the afternoon 2 online lectures, one from CICE in Turkey and one from Japan. So Satoshi Yoshida is one of the top guys in the world on mechanical properties. He'll be waking up at 5 a.m. in Japan to give a lecture. So we have to be on time. That's my message. So I urge the speakers to keep their lectures to 50 minutes or so. So we have some time for Q&A, and then a very short coffee break. It's been very hard to harvest everybody back to the room after the coffee break. So today we have to be German-like, or not Brazilian-like organizers. So it's my pleasure to introduce Professor Pedro Rino. He has been working for many, many years on molecular dynamic simulations. In the past 15 years or so, he has been working, luckily, with glasses, molecular dynamic simulations of vitreous materials. Also, he is an expert on developing potentials, which is a key part of molecular dynamic simulations, a very tough part. So, Professor Rino, thank you very much for agreeing to give you this lecture.
Zanot told me to give a talk. I have here. It's not an invited talk, research talk, but for schools. So I will try to give some overview of molecular dynamics. I'm sure everybody has been heard about molecular dynamics. And I'm sure several of you work with it. So let's start. What's molecular dynamics? What is for? Is it good? Is it reliable? Can we have some information, useful information, which can help us to understand nature? That's the point. Molecular dynamics, in general, has several meanings. One of them is related to the spectroscopy, real particle motion. The other meaning is let's dynamics, the vibrational motion of atoms in solids. Another meaning is force field calculation to see the interaction in molecules. In general, the people from chemistry like to say that. I will talk about the computational of individual movement of atoms, molecules, in any kind of system, solids, liquid, gas, and see the computational time-dependent movement. Okay. The essence of molecular dynamics is to solve numerically any body problem. Doesn't matter classical or quantum. You will see, I will repeat several times this motto. Numerical solve any body problem, always, because this is molecular dynamics. Since Newton, any body problem is very important. It means how single particle dynamics produce a collective motion, and vice versa. Example, how the movement of the fluid near one object produces turbulent waves. For instance, how atoms in proteins move together so they can support life. For instance, how individual molecules combine to each other to produce a new molecule. For instance, how does a local disturbance in a few atoms propagate through the system as a whole? So these problems are very challenge. It's not easy to solve that. So when you choose a system, doesn't matter, crystal, glass, liquid, circulatory system, anyone, our idea is to understand that. I would like to tell you a small story just related to this. Our goal is to understand its property. There was a philosopher called Bertolt Brecht in German, 19th century. He wrote a novel about Galileo Galilei. It's 2 or 3 versions of this novel. In this novel, Galileo was thinking, wow, to understand nature, only God, because God created the nature. I'm not God. It will be very hard for me to understand the material I'm looking at. But Galileo thinking, I can create my own nature. In my own nature, I am a small God, and I can understand the nature I have created. When I compare the result of my small nature with the divine nature, and they become close, I approach God. It's not my words, this is Bertolt Brecht. It's really what we somehow are doing here, right? Okay. There are different ways to look at the system and its property. You can look macroscopically, just with your eyes, measure what you are doing. I can use it microscopically in some degree, or much further one inside the matter, right? So, first thing you have to do when you are studying a system, you have to classify the system. You can classify all body who fall down and things like that. And when you do that, you can find some model, your nature, to describe that a phenomenon you are trying to study. For instance, consider a cow. I want to simulate a cow. The first approach I can use is a spherical cow. Of course, I will lose information about horn, udder, tail, but it's an approximation. I can improve the model considering a cylindrical cow, and so on. So that's the idea. Given the system of object, I have to have a model to describe that material. When you classify the phenomena, in general, you have to do some idealization, because the nature is very complicated. And these are our model. In general, these models are described through some law, some theory, and in general, they are given by differential equations to describe that material. For instance, Newton's law, hydrodynamics equation, Maxwell equations, Schrödinger equation, and so on, right? So the solution of these theoretical differential equations must be used or for some phenomenological model or for computers. There is no way. So we can see that experimentally you observe the nature. Make models, create a model to describe. The problem is that this, in general, we have a solution only for very particular case, so, right? In general, we don't have anything. And the computer is now very helpful because they not only can solve the model exactly, but they can predict results using extreme conditions not allowed in the experimental fact, for instance. So these 3 points is very, they come together. Let's say, consider for instance the quartz. I can characterize the quartz you look macroscopically this. I can measure density, hardness, elastic constant. I have a lot of information just having my eyes looking at, right? Of course, I can have some internal information using diffraction experiments. So we can have these beautiful patterns of diffraction. But this is very helpful when you have a crystal, because in the crystal we will have symmetry, so we can relate this diffraction pattern with the internal arrangement of the atoms inside the material. But when you have glass or liquid, you have just a big mess, and it's very hard to understand what are these peaks, how they come from, and so on, right? And here, molecular dynamics can help us extremely well. This is another example, silicon crystal, silicon amorphous, completely different pattern. You can see that. These are typical figure we can see. If the intensity, the scatter light, if a crystal, you have very sharp peaks related to the order of the crystalline structure. If you have amorphous, you have just a big band. There is no information, simple information related to that. So the other description is going inside at the atomic scale. So you see inside the material how the atoms of this material are put together. So I can ask, entering the system, you see what it's made of. So we have to find out some mechanical model to do that. For instance, from outside, gas, ideal gas, you have these famous results for ideal gas. When you go inside material, you can say, is there any mechanical model to describe this kind of gas? That's the point. And the idea, yes, we can do that. Ideal gas, there are particles which are far apart to each other, the density is very low, there is no collision between them. If collision happens, this collision is elastic. So I can simulate my ideal gas through a hard sphere. The potential is just infinite at the contact. Then that is free. In this way, all particles are hard sphere, and we can solve these equations and have the solution from the internal point of view of the ideal gas. But when you go sodium chloride, there are charge transfer between atoms. So hard sphere is not useful anymore. There are some Coulomb interaction. But now I have another problem. Because I have sodium plus chlorine minus, they want to collapse. They want to be closer and closer and closer. So my model to describe sodium chloride must avoid this collapse. So I have to put some kind of a repulsion in order to avoid this collapse you are putting. So the potential mechanical model for sodium chloride must have something like Coulomb interaction, repulsion term, and the total force will be the sum of both. So you can see I have a minimum, the system can be stable like that. Okay. Choosing the system, looking from inside, is necessary to have a mechanical model. This is the interaction potential, how each particles inside your system see each other. This is the approach to my call, right? So, now, next step, after, which kind of interaction potential I have to use? Only pair potential? Do I need a three-body interaction? Do I need a four-body interaction to see for biological molecules, for instance? Classical or quantum, do I need to consider interaction with the wall of the container? So, the most general form of one interatomic potential can be written like that. One-body interaction, two-body interaction, three-body interaction, and so on. If no external field are present, you don't have this, you have a general expression for the potential of interaction of material. This is one example of two-body interaction. Lennard-Jones. You have a very repulsive part plus one dispersion part, attraction part. You can see, go to Google and ask interatomic potential, you can find tens of interatomic potential in the literature. From hard sphere, Born, Buckingham, and bad atom, each one of these potential was created for a specific system and then generalized or used in another system. For instance, Stirling-Weber was proposed to describe silicon, amorphous silicon, liquid silicon, and so on. Brenner was proposed to describe the different kind of hybridization of carbon. Again, if I know the potential, I have the potential here. Now I have 3n equations of motion. Each particle interacts to all the n minus one other one, and so I have to solve this 3n equation of motion for the system. This is molecular dynamics. We can go home, take our coffee, because that's it. Finish. Of course, there is a lot of technical detail to do that. The first question, classical dynamics? Yes, we can do classical dynamics. If you compute the Broglie wavelength, and if you compute the average distance between particles, when I compare both length, if this ratio is almost 1, you can see this is the quantum regime because you can have a diffraction, we have things like that. If it is smaller than average distance, you have the classical one. If you take one car 100 kilometers per hour, you can see that the average distance in our life is meters. You have 5 meters, 1 meter, 2 meters, right? So the car is classical object, you can be sure that. But if you take one electron moving 1% of speed of the light, the de Broglie wavelength at 7 angstrom. So if you look at metals, the average distances of the atoms in metal is the order of angstroms, 5 angstroms, things like this. So electron, you have to take care. You have to consider quantum effect on that, right? Even sodium at room temperature is already classical. There is no problem about that. So the heart of molecular dynamics, you can see it's a devil, satanic heart, because if this guy is not good enough, all your results are screwed up. Right? If you know this guy, I have, as I told you before, I will repeat this every time because that's the essence of molecular dynamics. I have to solve 3n couple differential equations. So I need 6n initial condition. Why 6n? This is second derivative, so I need 2 initial conditions for each particle, position and velocity. What you can get? The only thing molecular dynamics gives us when you solve 3n differential equation is the phase space trajectory. That means position and momentum as a function of time. That's the only thing computer gives to you. So, put your interaction potential, put your initial condition, put one integrator, and you have all the trajectory. That's the message for that. What can we get? In principle, everything. If you know the phase space for all atoms, we can use the information from statistical mechanics, and you can compute temperature, pressure, total energy, enthalpy, elastic constants, bulk modulus, vibrational density of states, viscosity, name it. You can see everybody. Because in mechanics statistical, this is, all the information is related to the phase space. Is it easy? No. This is another problem, right? So, this is the first problem we have to solve. When you have this equation of motion, there is no way, there is no algorithm to solve this equation for 3n coupled differential equation. So the solution must be substituted by finite elements. If I know some initial position, I can compute it one instant further, solving the propagation. This is one simple way to show the propagation of this momentum E position. Of course, there are several integrators in the literature, since Euler until predictor corrector, leapfrog, Bayman. And this is very important because there's a lot of physical reason why this is important. They preserve the volume in phase space, and they come from the propagator, Liouville propagator. There's a lot of stuff. So, two orders. I need initial condition. Position. I have to give the position for all particles in t equal to 0. There's two ways you can do that. Just random, or I can use crystalline position. The velocity of all particles, I can just say all particles have 0 velocity, or I can use the Maxwell distribution to distribute the velocity among them. Right? Why the crystalline structure is interesting to start with. In a BCC, you have just 2 atoms in unit cell. So the coordination of this atomic position is very easy to get. If it's a FCC, I have 4 atoms per unit cell. So if I know the coordinates of one unit cell, I can repeat how many times I want in 3 directions. So I can generate my system, so easily make the translation of unit cells in all directions, and you have the total number of particles. If it is random, you must take care, because when you put randomly the particle inside the system, it's possible that 2 particles very close to each other. So the interaction will be very strong, and you will have some problem. Okay, I can create one algorithm to not allow this kind of stuff. But starting from crystal, if my potential is okay, I can study the melting of the system, for instance. This is because I have to propagate, I need how much is the time step necessary to start from the position, generate the next one. Dimensionally, you see the Newton's equation, we can see that mass, length, time square, energy length, I think that the time is related to this quantity. So this time step must be a fraction of the characteristic time of your material. When you take, for instance, argon, you have a mass, you have energy, the characteristic term is 10 to minus 12. So to use molecular dynamics for argon, I have to take one fraction of that. That means time step should be 10 minus 14 seconds. In general, people use 1 femtosecond. You can ask, how long you take to follow the system for 1 second. Because this is time to minus 15, I have to integrate to propagate the system 10 to 15 times. It's a lot. I just did this in my personal desktop. It's a Pentium. 8,000 atoms, 1 time step is 0.036 seconds. If I have 64,000, 1 time step is 0.37. So, in 1 second, I have something like 1 million, 11 million years to see the propagation of 1 second of your system. What I'm trying to say, molecular dynamics is very short in time. All results you can obtain is very short in time. It's the order of nanoseconds, maybe milliseconds, no more than that. The system size to be simulated. Possible size and time are very crucial. For instance, take the diamond. The only cell of diamond is 25 angstrom, and we have 8 atoms. If I multiply that per 1,000, I go nano cubic. And if I have a micron cube, I have 8 to 10 6 atoms. So the simulation also is related to the size of the system you are considering. It's impossible nowadays, with the computer facility we have, to simulate a system with Avogadro number of particles, right? The record of simulation starting in 1957 with the hard sphere. They have a computer of 1,000 flops. They simulate 100 particles. Cadal, in 2006, they simulate Leonard Jones system, 320 billion particles using a teraflop machine. In 2012, Vachista, using a real potential, potential for describe silica or silicon nitride, they use it to have it to almost 200, I don't know how to, in petaflop using 218 billion particles. These are the records I follow until here. I don't know, I haven't seen any other record about that. So, in my group, in general, I use simulations with some 1,000 particles, but I have simulation with 1 million. I have a small cluster, we could simulate that. Okay, more technical detail. I want to study wine. What is the property of wine? Is it inside the cup? What is the cup made of? How does wine interact with the cup? When you have a system, you have a box, volume is L cube. The fraction of particles in contact with the surface is proportional 1 over L. So the fraction of particle is proportional 1 over square root of 3 of number of particle. If the number of particles is very hard, you can see that the fraction of particles close to the wall is neglectable. You can ignore that. But if the system is small, about 10% of the particles are in contact with the glass. So we have to eliminate the effect of surface if you want to know wine property. Right? To do that, you use periodic boundary condition. And the periodic boundary condition is very simple. You make image of your system infinity direction, and always when one particle leave its image, go inside. In this way, we eliminate the surface effect. You have information only about your system. It's important to emphasize that this is not, periodic boundary condition is not the limit, thermodynamic limit. There is nothing to do with the thermodynamic limit. It's just surface elimination. That's it. Of course, I can have a vacuum everybody, so I can study one piece, one block. Or I can make one wide, or I can make one sheet. You just can create a different periodic boundary condition. Okay, you have the force. When you have your potential, the force is the derivative, so the component x of the force in the particle I will be giving you an expression like that. So, there is a compositional effort, it's wrong here, n squared, because I have 1 interacted with n minus 1 here, and so on. You have 1 effort. That's it. The particle 1 interacts with all the other particles, the particle 2, and so on. Because we know action and reaction, I don't have to compute all these metrics, but just half of it, because this force is just the minus of this force, and so on. This make the computational effort a little bit small. Of course, we can do better, create tables, create a neighbor list, so then there are technical details in order to decrease the number, the time necessary to propagate your equation of motion. Okay, so we have boundary condition, the size, one sample considered, and what I have to do, put it initial condition, calculate the force, propagate, apply periodic boundary condition, call force again, store the consider, and you have to run this for how many times you can do that. And when you do that, you compute your average. This is the block of your material. Okay. The point is, how I know the interactomic potential is correct? How I know the model I am choosing describe the call, right? I must go to measure some quantities, and for this I need to compute several quantities. For instance, if my system is isolated, we call microcanonical ensemble, these quantities are constants, should have constant energy, should have linear momentum of center of mass constant, and should have angular momentum constant, right? In particles, we need, in statistical mechanics, we need one ensemble, so the average is one average over the ensemble you are doing that. In MD, what we have is the evolution of phase space. So my quantity, my average, is one average on time. These two, average on time and average in ensemble, are the same if the system is ergodic. That means if I allow enough time to visit all the points in phase space, these two averages are constant. We don't care. We say the system is ergodic because it's just what you want to, this is just what we know how to do. So we impose the ergodicity of your system. From equipartition theorem, we can obtain momentum here, the temperature. What is interesting, I can define an instantaneous temperature. And of course, the system temperature will be one average on the time. It's very nice because you see how the particles go to equilibrium when you follow the temperature as a function of time. It's a lot of noise, but see, this is 26, this is very small stuff, not too bad. you can fit one linear equation. You see the angular part is -5, right? It's almost 0. This is for strontium titanite. The system is in equilibrium, so all the 3 temperatures are the same. Okay? Pressure. Pressure is very easy also because I have the equation of the virial. So the pressure is proportional to the coefficient of the virial. And again, I can define an instantaneous pressure, and the total pressure is the average of that. And see, I start the system with some internal pressure, the system evolves to pressure 0. This is another important, fundamental result property from the materials. It's called pair correlation function or radial dispersion function. You sit in one particle, and you measure how many particles are in a shell of radius r plus dr. So I can measure this quantity here, and do this for all the particles, and you have the G of R. The area under G of R gives me the coordination number, and the total part distribution function depends if I have more than one species, depending on the concentration of species alpha and beta, and you have the total G of R. A typical curve for G of R, if a crystal, it reflects the position of the atoms in the crystalline structure. This is the first neighbor, second neighbor. In red is the coordination number. You see the first coordination number, second, and so on. If you have amorphous or liquid, there is no order, long-range order. You have just the first peak, which is related to the... Deu com problema, tá bom. And of course, for gas, you have something like that. Why this is important? The partial G of R. If you look just the G of R, G of R alone is not enough to give the information, complete information of your system. The partials allow us to accurately determine the coordination numbers who contribute to the total correlation function. These partials plus angular distribution, you give the complete description of the material's structure. This is one example, silicon carbide. This is the total G of R. This is the partial G of R. We can see just this peak is related to this. This peak is a sum of everybody, and so on. When you have amorphous, you have completely different. Here you have a very clear coordinations of each one of this material. Another example of the three-body correlation is very simple. We have 3 positions, A, B, and C. We have this vector, R2 minus R1, R3 minus R2, R1. So I can make the dot product of these 2 vectors. When I do that, I can compute this angle we have here. 5. And this is one example. For if a cubic, I have just one angle, 90 degrees. Remember this number, 0.07. If a FCC, I have much more angles, the same number. The difference between BCC and FCC is just the distribution of angle. If I look just at the G of R, I will not know what's going on there. BCC, HCP, and this is one small example, zinc telluride. I'm putting pressure, hydrostatic pressure in your system, and the size of MD will decrease in time because you are squeezing it, and suddenly they change in this form. I can characterize before and after this transformation. Computing partial G of Ggen at zinc blend and go to rock salt. This is bond angle distribution, G of R. You can see that at the beginning, from 0 to 10, you have just compression. The first peak, which is related to the bond length, decreases. And when the transformation happens, the bond length increases, and the coordination number increases, and the bond angle show what is before 109, typical of zinc blend, to two other points. The structure factor we can measure experimentally is in Q space, reciprocal space, molecular dynamics in real space, and should be made a Fourier transform to connect that. So there is no way to say that my model is describing this system if the result I got from MD do not describe what experimental observe. So this comparison of the structure factor from experiment and the MD must be matched together. So I can say this model for silica describes correctly the structure of the silica, real structure, because you have the same experiment given by that. I can do dynamical part, I can compute velocity autocorrelation function. I can also see things like that, right? And just to finish, because Zanotto told me I'm short in time. First, this part here. Go to web, you can see lots of program of doing molecular dynamics. Also, you can create your own molecular dynamics. This one here, LAMPS, is fantastic. You can believe on it and give you, you can see also several interatomic potential put in there by the people. It's checked, it is good. LAMPS, in my opinion, is very, very, very good. Just to finish, I would like only to show to you my ongoing project. I use this interatomic potential to describe orthoinstatite. Orthoinstatite is a mineral which has several crystalline phases depending on pressure, temperature. Here I have the Coulomb interaction, which is screening, repulsion, charge dipole, and dipole-dipole interaction. I found one set of parameters for orthoinstatite, and when I compute the volume of my simulation with experimental volume is very good, only 0.8% higher. This one here is just where the minimum of energy happens, which volume, and you see it's also described relatively more or less equal, good. The vibrational density of states for crystalline also have the same range of energy, you have all the same bands reasonably well. So I heat the system, here's volume, I heat the systems melt, mechanical melt. And this is density. The density decreases because the volume is increasing and you have melting. When I cool it down, the volume is not returned here, I have one amorphous immaterial. The interesting point is this 2 point here is that from my simulation at 300K, the density of the material is 0.08 angstrom -3. The experimental density at 300 reported by Phil Salmon as 0.079. So without any kind of adjustment, my potential described the correct density for amorphous at that point. More than that, and about the structure, I have to compare with good information from diffraction. This is the, again, Salmon data. We have a X-ray structure factor compare with my simulation. Show that my structure not give my potential gives not only the density correctly, but the structure of this material very well described. And recently, Rafaela and Pisani measure for glass the Raman spectra. We can compare with our vibrational density of states, say that the result is very nice, right? And is model good? Depending on mechanical problem you create. The fashion today is machine learning. I am completely ignorant about that stuff. You have to talk to Daniel Casar, who will talk something about that, right? So to finish, moral of story. Give me a lever, and I'll lift the word. I can say, give me a good, the real interatomic potential, and I give you all answer you want. Okay? Thanks.
Thank you so much, Pedro, for this extremely nice introduction to MD simulations, which I guess will be followed by Colin and Rebecca showing real applications to problems of interest in glass science. But before we move, we still have time for some questions. Yes, student here and then Professor Ben.
Hello, Professor. Thank you for your presentation. I have a question about have you ever developed the potentials, the MD potentials, and what is the general process? Yeah. Have you ever derived MD potentials? Develop MD potentials?
I'm not sure if I understand.
Yeah.
If he has ever developed a potential?
Yeah.
Well.
How to develop? Okay. We use a lot of physical intuition. For instance, this is the term, which is the charge-dipole interaction. That means each ion has a charge, and each atom has some electronic polarizability. So this atom interacts with the electronic polarizability of this other atom. And the interaction will be electronic polarizability times charge square. It goes 1 over R4, and always attractive, right? So I can factorize charge in this potential. When I factorize charge in this potential, of course I will redefine this in terms of the charge. The charge defines the scale energy of your material, right? So when you compute vibrational density of states, this scale of energy is related to the size of the charge you choose. If you put your charge too high, this scale will go there. It's too slow, you come here. Of course, only the charge will not finish the determination of potential. When you look at the other term, this term here is just the term of contact to avoid the collapse of the system. So the intensity of this term will define bulk modulus, because bulk modulus is just the contact of your atoms. So changing this term, you can adjust the bulk modulus of your material. Of course, you have to do this measure this, and so on, right? Until they'll have a minimization of this effect. This term is also attractive. It's very important because if you put too high value of H, the pressure of your system will be very high because you are putting a lot of repulsion. So the pressure will increase. So I can adjust W in order to bring back the pressure to 0, right? So these three values, charge, repulsion, and this one, you have to play with them in order to find the parameters for this formula, right? For this formula.
Yeah, it's a lot of going back and forth, back and forth, back and forth. It can take a long time, you know, to really develop the potential. So Professor Ben, and then I have a question here.
Thank you, Professor Reno. I'm curious, could you go back to the density of states where you showed the MGO-SiO3 simulation of Pisani and Raffaella, or your simulation and their Raman spectra? My question for that is, normally we have a temperature correction and all the low frequency stuff gets dampened quite down. But your density of states was showing it quite large and comparable to what was measured experimentally. Could you comment on whether that is real or whether that is taking the temperature correction into account? Basically, how well does it match at low frequency?
The result is a little bit, they are complementary. My curve here is the vibrational density of states. You have all the modes involved in your material. Raman is only particular stuff you have there, right? So my point is, these modes in Raman are reproducible there. But why the intensity here, I don't know.
Okay, thank you.
This is how I keep fit, you know, coming.
Thank you, Professor, for your presentation. My question is related to the chart where you showed the experimental studies and the MD simulation. So my research is on glass ceramics. Yeah. So I want to know how can we utilize MD simulation to predict nucleation and growth of crystals within the glass ceramics during the crystallization process, and how can we use these simulations to integrate the experimental studies as well as to optimize the thermal processing route for magneto-optical applications.
You are very ambitious. Very big. The first part you can.
The first part you can. Yeah, yeah. I have developed one very good interatomic potential. I have developed one very good interatomic potential for zinc selenide. And why zinc selenide? It's a semiconductor, has several interesting properties. We can show that it's very good. When you melt the system, we have and cool down. There is size independent. We have two windows, very low silicon supercooled liquid and high supercooled liquid. Our system allows us to compute in this region here, my system shows spontaneous crystallization. So we can measure the
solid light particles using this parameter they call Steinheim bond order parameter, right? When you do that, you see very low temperature, you have to see a small group of crystalline particles, then again increase, the temperature is higher, the seed will appear only farther on, and if you increase more the temperature, you have to wait more than that, right? So we can show that first, the spontaneous crystallization is one random effect. It starts here, goes there, everywhere. So you can see that in this case, the particle make one cluster, one small size, and dissolve because they don't reach the minimum radius to grow. And suddenly they grow and do that. We can follow this with MD easily, just computing the Steinheim bond order parameter, you follow along the time of your material. But to do that, your potential must be able to reproduce the spontaneous crystallization. If you don't have spontaneous crystallization, you will not be able to observe that, right? And few potentials I know show spontaneous crystallization, right? Germanium, there is one guy who created the potential for germaniums, and they show that is so good.
Thank you.
The other part, I'm sorry, I never talk about that.
And you can also measure the growth rate, you know, following the size of the particles.
You can
Nucleation
measure,
growth.
You can measure the velocity.
In the overall crystallization and everything. But it's exactly 9 o'clock. So let's leave your question, please, to the coffee break, to Professor Rino. Today we have to be more strict with time. Now I have the pleasure. Thank you very much for it. It's now Professor Colin Wilkinson. He has been working for many years now on using different techniques, computer simulation techniques, to understand different phenomena regarding glass science. So thanks very much, Colin, for coming all the way from Alfred to São Carlos. Valeu, foi bom. Obrigado. And, okay. Colin, please. Thank you.
Awesome. Thank you so much, Edgar. And thank you so much for having us. We're excited to be here. So today I'm going to talk a little bit about relaxation. And so I have a rough outline. Is that going to work? It helps if I turn it on. There we go. So I have a rough outline. My plan is to give a brief introduction to the glass transition, tell you a bunch of lies, and then explain the lies in such a way that we can make something sort of cohesive out of the relaxation literature. It's fine. We're in good shape. So if we start, as we should, with a definition, right? And we can look at Edgar and John's definition for what is a glass. Right, Lauren? That's where I always start, right? So if we actually break this down, there's two main things that we really have to worry about. Inside this definition, there are two phenomena that are really happening. We have relaxation and crystallization, right? This definition is defining a glass based on how it evolves towards a supercooled liquid state and based on it not having a crystalline structure. So when we really think about the origin of what we think of as glass, we have to think about these two processes, relaxation and crystallization. I think it would have been rude for me to sign up to give a crystallization talk, you know, in Brazil, so I'm happy to talk about relaxation. And so to start with understanding relaxation, we have to actually understand the first process. So when you melt a glass, right, you quench it and you push it down, and it's leaving the equilibrium state, the metastable state, and it's becoming non-equilibrium. And this is the process of the glass transition. So as you go from the supercooled liquid to a glass, you are going through the glass transition. And the opposite of the glass transition is glass relaxation. So as you go back from being a glass back to the supercooled liquid, this is the process we're calling glass relaxation. Good so far, Adam? Yes? Good. Okay, so this relaxation is at the heart of everything we care about, right? Oh, wrong slide. So what we're really worried about is how do we understand this? And how do we paint a picture that is cohesive, quantitative, and really tells us about the underlying physics, right? Because the underlying physics of relaxation are inherent to the underlying physics of what is a glass. So one picture that I'm going to paint you today is called the energy landscape model. And the idea here is that you find a bunch of different arrangements. You find all of the different ways of arranging a glass, and that tells you about the energy of that structure. And you can define these as what are called the inherent structures. So these local minima are going to be really, really important to understanding the physics of what glass is. And we can actually then define, based on the local minima, a Hessian, get your eigenvalues, and if all your eigenvalues are 0 or positive, you found an inherent structure, a structure that matters to understanding the evolution of a glass structure. I'm going to show you this in 2 different ways today. First, I'm going to show you this kind of drawn-out landscape, but I'm also going to show you what's called a disconnectivity diagram. And the way to think about this is that this minima is the same as the end of this line. If I wanted to find the barrier from going from here to here I would just draw it up, but here I would go up, find a crossing line, and then trace it back down. Why? Why am I showing it to you in 2 different ways today? Well, that's because a real disconnectivity diagram looks like this. So this is what a real energy landscape looks like for silica. So each one of these terminating endpoints is a way of arranging a silica glass, so SiO2. And so if you wanted to go, say, from this structure over here to this structure over here, you would trace up, trace down, and that would tell you about the energy it took to move from one arrangement to another. It's really important to note that this change is not a single process, but each one of these lines represent an entire arrangement of your entire system. So usually we map these out from molecular dynamics or some other molecular modeling technique. Okay. Whoop. There we go. So let's go back to our simple case. In this simple case, we can picture several different energy states, right? You know, for example, this first one could be, let's say we have 4 silica units and 4 sodium ions, right? Something to create Q units. So in this case, we could have 4Q3. That might be the lowest energy structure. Maybe that's why we see it in crystals, right? Up here, we have a little bit of a distribution, 2Q3, 1Q2, 1Q4. And then up here, we could get something really crazy, right? Like 1Q1 and 3Q3, right? It could be really crazy distributions. But the important thing is that we're actually mapping out all of the possible arrangements. We're not just looking for one arrangement, we're trying to find all of the arrangements. And so what happens is, when we actually take our energy landscape and we quench it, when we start looking at it as a function of temperature, we can define our entire system as one point on our energy landscape. So just as a reminder, that means that this is 3 n-dimensional. And Jacob, you might be like, Colin, why didn't you just draw it in 3 n dimensions for us? One day I'll get good enough to be able to do that, but that's not today. So if we look at the system, which is represented by this purple dot here, at hot temperatures, we're able to sample the entire system. It's an ergodic experience, right? It's an ergodic system, so we can sample the entire phase space. However, as we continue to go down in temperature, we start to have more and more sluggish kinetics. We can no longer overcome things at the same rate that we used to be able to. And then as we go to very low temperatures, we can no longer escape our basin. So at some point, we become trapped. We are no longer able to rearrange and become a new structure. And that point of being trapped is the most important point for understanding a glass. It's also important to realize that when we think about the point of becoming trapped, it's not just about time, or it's not just about temperature, it's also about time. right? If I, lock you in this room and say you have 1 minute to get out, you're probably not getting out. But if I lock you in this room and give you 3 days, you might be able to get out, right? So it's important for us to not just think about temperature, but also the time component. So when we define the glass transition, the process of being trapped, we have to incorporate both of these ideas. And we often do this through what is called the Deborah number. The Deborah number is a biblical reference about the mountains flowing before God, right? And the idea behind that is if you're a creature, or if you're some entity that would live forever, continents would look like they're continuously moving, right? And that's allowing the continents to move, allowing it to change, allowing things to morph under that long time period. However, if we're an ant or some sort of insect that lives one whole day, even things that seem fast to us as humans seem very slow to these small creatures, right? So it's not only about the temperature of the absolute process, it's also about our ability to perceive the rate at which this is happening. This is a really hard concept at first, right? Because usually when we're talking about physics, we want to talk about absolute truths, right? We want to talk about things. But as we talk about non-equilibrium processes, it is so subject to the actual conditions of the experiment, to the actual conditions that you go into the lab. So we can define based on the Deborah temperature. So this is, you can think of this top number as the average time it takes to leave a basin, and the bottom number as our observation time. And so we can define the glass transition as the point in which this Deborah is equal to 1, or this relaxation time is equal to our observation time. So this gives a very fundamental definition of the glass transition, but a very impractical one. Because as it turns out, it's not so easy for us to all standardize our observation time, and it's not so easy to measure relaxation time consistently. Right, Ricardo? Ricardo will tell you all about it at his poster. And so what we do is we start to make some approximations. First thing we do is we fix our observation time. So when we do experiments now, we try to fix our observation time to 100 seconds. Why 100 seconds, you might say? I don't know. Austin Angel said so we're going with that. So we fix the observation time to 100 seconds. And then we can also use this handy equation, where g is the shear modulus, approximately 10 to the 10th. Move that over there, 10 to the 10th times 10 to the 2nd gives you 10 to the 12th. And that gives you a viscosity definition, right? A definition for where the viscosity is defining the glass transition. And this is a very helpful definition, right? Because now we're no longer based on this observation time through a couple steps. We've been able to quantify and give a firm definition that when the glass forming system reaches a viscosity of 10 to the 12th, that's the glass transition temperature. But of course, what is the most common way to measure the glass transition? Who's measured the glass transition temperature? Yes, how do you measure the glass transition temperature? Yes, exactly. DTA, DSC, some sort of calorimetry technique is the standard, right? That is at least the most common technique we use in our lab. I'm sorry? CTE is actually a very similar idea, and we'll talk about that in just a second. And so what we see is that we actually, when we measure a heat capacity or a DTA signal or a DSC signal, what we have is we have a contribution from vibration. So this is the underlying matrix vibrating in such a way that the Debye or Einstein model describes. And what happens is, when our system is allowed to move between the basins, we get a new contribution, this configurational contribution. This configurational contribution happens at the exact rate where we start to see this interplay between these models. The point at which the system can start exploring the different basins. And so we measure, often, the glass transition as the inflection point, as corresponding to the Deborah number. So this all traces back, no matter what definition of the glass transition you choose. I shouldn't say that. Most definitions of the glass transition trace back to being able to be identified based on this idea of relaxation, or the Deborah number. So let's actually get into relaxation. Glass relaxation has been observed since the 1800s. It's not new. But we're going to spend most of our time talking about the models behind glass relaxation. There's a lot of challenges here. And so I'm going to explain to you the kind of the standard model, and then we'll go from there. And so the standard model really starts with this guy named Toole, who I just recently found out is from like near my hometown, which was kind of exciting for me. And so Toole was working at the forebearer to NIST and was really interested in how do we explain the variation of volume with temperature and time? How do we actually understand this? So Toole proposed this equation, right? And this is essentially an exponential decay order parameter. And this equation is based on the idea of fictive temperature, fictitious temperature. So in short, there is a real temperature at which our system is at, and then there is a fictitious temperature at which, if the system was heated instantly to, it'd be in equilibrium. That's a long definition, so I'm going to say it again. There's a real temperature, like the temperature of this room, and then there is a temperature at which, if you heated it to, it would immediately be in equilibrium. Okay? And so Toole said it evolved according to relaxation, according to this expression. This is actually a QR code with a little calculator, so you can go online and download a little Python script that I wrote that will allow you to play with different Toole parameters and be able to calculate relaxation for fun, as you do. And what you get is this is a system that is quenched. It has a TG of 550 and a fragility of 55. And what you can see is you quench it at different rates and then heat it back up. And on the cooling, you get the nice curve, and then on the heating, you get the overshoot. And so you can see how this changes with different different quench rates. And then over here, we have the derivative plotted. The derivative of the fictive temperature is often correlated with an actual DSC signal. So what we can see is we can see a cooling rate and then a heating back up. And this gives us an approximation for the DSC. Nice, right? Not bad, 1930s, early 1940s. Toole was doing this all by hand, no computers. Incredible work for the time. Really excellent. I want to make a quick note that Toole is introducing the idea of fictive temperature, but we also use this idea of fictive temperature on VT diagrams, right? If you take your Intro to Glass class, I'm sure you spend a lot of time talking about VT diagrams. And it's really important to note that this fictive temperature on this VT diagram is the point where you're leaving the line. It is a qualitative description, while this fictive temperature, Toole's fictive temperature, is supposed to be quantitative. So when we discuss fictive temperature, it is often that these two are conflated. This is a great qualitative description to talk about, and we're going to talk about some of the limitations of this. Okay. So Toole published that original work in the early 1940s, late 1930s, and then not long after came along another scientist, this time at Corning, Ritland. And Ritland was really interested in specifically making really big lenses without aberration. And so they really needed careful annealing to make sure that they have high quality glass. And what they found was that they were having issues using Toole's formalism. So Ritland put together an experiment. He measured the refractive index of two glasses. One glass that was cooled at such a rate that it should have the same fictive temperature as another glass that is annealed and then cooled. And what you find is here's the equilibrium line, the annealed one, and then here is the actual one from the cooling. And what you can see is it starts at the same point and it ends at the same point at infinite time, but it actually moves away and then comes back. This is called a non-monotonic decay. That's your vocab word for the day, Jacob. Great. Non-monotonic means that it's not one direction, it's multiple directions. And this is a huge problem, right? If we look at Toole's formalism, TF always goes towards T. End of the discussion, right? Here, in an isothermal hold, that means that you should never move away from the equilibrium. But this is exactly what Ritland described. And this presented a huge mathematical challenge. How do we actually deal with this? So there was a new model proposed called the Toole-Narayanaswamy-Moynihan model. Narayanaswamy was working at Ford and was also trying to solve this problem for tempering and for understanding windshields. And so Toole-Narayanaswamy-Moynihan model, they thought, right, if one fictive temperature doesn't work, what should we do? What could we possibly do to fix with one fictive temperature not happening? You just add more. So they started adding more and more fictive temperatures that make a fictive temperature distribution. Okay, I guess that works, right? And if we look at their model, you can clearly see that they can reproduce the Ritland experiment now. So from here, they're able to actually start to describe the non-monotonic decay by looking at a distribution of fictive temperatures decaying. There was a couple other corrections that needed to be applied. The original formalism from Narayanaswamy was effective, but not very easy to calculate. So here was an update for making it easier to calculate it, bringing it into a more useful differential equation formalism. The relaxation time wasn't quite right, so the MAP model worked on updating this, the Morrow-Allen-Petuzak model. And then over here, the stretching exponent. So it turns out that distribution of fictive temperatures gives different shapes of relaxation. And so we needed to estimate the different shapes. And so we applied that correction as well. And the great news is, you can download this model, all implemented together, and run it. It's pretty straightforward. There's some approximations to get all the parameters. You can enter any theoretical thermal history curve and get an answer. It's not crazy. That's nice, right? We go all the way from having this kind of fundamental idea all the way through an implemented code that anyone can download, open source. It's useful. So why should you care about relaxation? Why would this be worthwhile to getting into? Well, it turns out relaxation is a huge driver for manufacturing processes. If we think about annealing, this is the rate at which stress is relieved, right? This is inherent in the problem of relaxation. If we think about modern LCD or modern displays, you make a sheet of glass, and then you start embedding pixels at high temperature. And over time, this glass contracts. And so your ability to place pixels actually has to account for how the volume of the glass changes while you're doing the process. If you don't, you can't make the high resolution displays that we're very used to. Stress in optical fiber, of course, is inherent related to relaxation. Ion exchange and tempering, those you're actually trying to avoid relaxation, right? You want to imbue stress, so you have to understand how to avoid relaxation to actually make your glass stronger. We also know that relaxation affects almost every property that we care about. There is an inherent problem in making a good model, or every property that we care about from a glass manufacturing process, from a glass use process, is influenced by relaxation, or at least everyone I know of. Cool? And it was happily ever after, right? No problems. That model works great. There's no problems. We can close our ears, close our eyes, and call it a day. Right, Ricardo? Ricardo says yes. He's very happy with the answers. No. So here's where we get into the truth. So this process does what I told you is correct. You can make that relaxation model. You can download that code. You can make the approximations. But there are at least three, from my point of view, three lingering issues that are not so small, that are completely glazed over by most of the models that are out there today. The first issue is that there's not one type of relaxation. This is a huge issue. When you look at the historical work and even the MAP model, it conflates all relaxation to either happen on approximately the same rate or to be caused by the same underlying mechanism. But if we actually go back and look, there's a lot of historical work that shows that there's actually more than one relaxation peak, right? So this is looking at temperature versus the loss modulus. And I believe this is DMA, dynamic mechanical analysis. And what you can see is that you can actually see 3 different relaxation peaks arising. Some people say that there's even a 4th one way down here. This is also stress relaxation. It's important to note over here that there is at least stress and structural relaxation. These are 2 different processes, right? So the rate at which you relieve stress of your sample is not the same rate at which the sample progresses towards the equilibrium. And in all of the models historically, at least prior to 2020, they conflate the 2, that they are happening due to the same underlying process. So this is a big theoretical challenge and a big challenge of practical import, right? If you want to know how to lower the fictive temperature, it turns out that's a different rate than the rate at which you should be annealing. It's a large challenge. It turns out, depending on who you ask, there are between 2 and 7 types of relaxation. I'm not sure I'm on 7, but I'm definitely not 2. I'm somewhere in between. So there's the ability to actually distinguish these and test if they're unique, and if they exist in all glass-forming systems, as far as I can tell, is still an open challenge. This was particularly highlighted from a theoretical paper from Karan and I, where we compared the stress relaxation to the Maega model to the MAP model. And you can see that the stress relaxation lines up really well with the MAP model. And if we look over here, this is what the MAP model predicts for structural relaxation, and these are the actual data points. And so you can see that the MAP model is working very well for stress relaxation, but is actually struggling quite a bit for structural or enthalpy relaxation. Over here, this work was repeated and done slightly better than our original work for the experiments. Thank you, Ricardo. And Ricardo and Edgar and Danielle also were able to repeat this with a couple more data points than the 3 we got from literature. So we were able to show pretty conclusively at this point that stress and structural relaxation are 2 different phenomena, with our description missing in action. We can't accurately describe what is happening. So takeaway, the models prior to 2020 are conflating these things. And when you use these models, you have to be very careful about whether you're trying to predict stress relaxation or structural relaxation. Cool? All right, 2 more. Fluctuations. Another challenge with fictive temperature approaches, or this approach, is that fluctuations evolve. So this is a really nice work from John and Sabyasachi, where they looked at samples annealing, and they looked at the actual evolution of the density. And you can see here, this is the equilibrium, and you see very nice curves, right? You see very nice classical relaxation curves. The challenge with this is that when they measured the fluctuations of the density, it evolved non-monotonically, while the density itself evolved monotonically. I told you, Jacob, it's a great word. Every night I say non-monotonically like 5 times before going to bed. That's a joke. I don't actually do that. Yeah. Okay, so what you can see is that this is a challenge also, because there are some properties that really depend on density fluctuations. For instance, Rayleigh scattering is not driven by the density itself, but it's driven by the density fluctuations. Same with fracture toughness. As far as I can tell, a lot of the modern models look at fracture toughness from a fluctuating point of view, not from an average point of view, which means that overall, to be able to predict properties on relaxation, we have to predict not only the average, but we also need to predict the fluctuations. And if we were to actually look at this, we wrote this paper looking at the fluctuations of fictive temperature. And this would reproduce, this is an example of like time with different fictive temperatures, and over time, because they always approach the same temperature equilibrium, by default, any model based on fictive temperature, like the Tool Narayanaswamy model or the MAP model, reduces fluctuations with time, monotonically. So even though the Narayanaswamy model has corrected it for the average, the actual fluctuations are still not correct. As a matter of fact, the Narayanaswamy model predicts that there is 0 fluctuations in the limit of equilibrium, which of course is doesn't make sense, right? Yeah? Cool, thank you. I was looking for some thumbs up. All right, so that means that these fluctuations are really important to being able to predict properties and understand what's happening. When we think about, yeah, that's great. Okay, last one. River, are you excited? I know you're scared. We'll get through it together. Okay, so the last one is fictive temperature itself. So when we think about fictive temperature, the order parameter by tool was proposed by fiat, right? They said, let there be some order parameter that is exponentially decaying. And this is a challenge, because it turns out if we actually stop and look at the physics and go back to our energy landscape, we can draw this really nice map. So I'm going to just spend a second on this, right? So this is your Boltzmann probability of occupying a state. P sub I is equal to 1 over the partition function times exp to the negative energy over KTF, approximately, right? This is the most physical, meaningful thing that I can think of for fictive temperature, quantitatively. And so you can say that there's some distribution, and then the TF describes what is the effective probability distribution on this landscape. And so what you get, over here, you can find all of the allowable states. So this blue area describes all sets of probabilities that are theoretically possible. There's some thermal history that will give me a set of probabilities over here. It probably involves infinite heating and cooling rates, but you know, who cares, right? That's Ricardo's problem. So if we then subdivide this, we can look at the actual equilibrium pathway, right? So the point where they're all equal, which is out here, where all 3 of these things are equal, is at infinite fictive temperature, right? If I put an infinity out here, you get 1 over infinity, that's 0. E to the negative 0 is 1. They're all equally likely. And then at 0K, right, if we put in 0, then only the lowest energy one is most likely. And so we define this equilibrium path from here to here. But for non-equilibrium, you can have anywhere in this blue space. But if we're defining our system based on summing up different fictive temperature components, we are limited to a linear summation of this equilibrium pathway. So what is the space that we can describe via fictive temperature? Well, it turns out it's only this space. Only in this space can we actually describe the state of the system as a linear addition of the equilibrium conditions. Everywhere else that theoretically you could have probabilities, it cannot be described via fictive temperature. Now, this is something I've presented a couple times, and the instant response I always get is, what is the likelihood that any actual glass we make is outside of this region? And the answer is, I have no idea. So whether this is a purely theoretical concern or if it is a practical concern about being able to describe something as a linear basis of fictive temperature, I think that there is still a lot of work to do from the experimental side to see whether that's feasible.
Just to clarify, I'm not sure if I understand the concept of allowable fictive temperatures. Like, from a practical point of view,
Yeah.
if you have a liquid, you can have any, talking about the average fictive, you can have any fictive temperature, right? For any cooling rate.
Right. So the idea here is that this corresponds to infinite temperature, this corresponds to 0 temperature, and the place you are on this graph tells you about the probability of occupying each one of these states. So when you're on this path, like, if this is true, then you have to have a Boltzmann distribution of states or a summation of Boltzmann distribution of states. And that summation of Boltzmann of distribution of states can only describe that yellow curve. While if you have a non-Boltzmann distribution theoretically, you can get something anywhere in this blue space.
Right. Theoretically, you can be anywhere in
The forbidden space you can't be because it require much higher occupational probability in lower energies or in higher energy states.
Okay. Thank
Okay.
you.
Though now people are doing vapor deposited glasses, and they claim from simulation that they can get into this forbidden glass space. Okay. The other way people have proposed is that fictive temperature is not actually describing the Boltzmann probability, it's describing a ratio of the probabilities. And this is from the French literature in the 90s. People were trying to argue that this is the case. The problem with this is then the number of fictive temperatures you need to make a prediction is equal to n squared minus n, where n is the number of basins you have. So there's an approximation out there that n is on the order of Avogadro's constant. So 10 to the 23rd fictive temperatures, why not? Why not? Right? So these are the three outstanding issues in relaxation. These are really challenging issues in relaxation. And of course, from an experimental point of view, these two types of relaxation and fluctuations are the largest challenges, right? To actually make sure that we're recovering the fluctuations really affects the properties that we're trying to engineer. From a theoretical point of view, from fictive temperature point of view, I'm not sure how much this description affects the experimental practical design of fictive temperature. I don't know. But there's got to be some theory there that updates that in some way. So recently, there's been two kind of main improvements. And I want to finish a little bit early so we can discuss a little more. The first is from Wataru and Pierre Lucas. And what they did was very clever. They said, yes, there is a distribution of fictive temperatures, but there is also a distribution of fragilities. And so if you have a distribution of fragilities and a distribution of fictive temperatures, you inherently get a distribution of equilibrium states. And so this leads to an ability to actually reproduce the fluctuations quantitatively based on this distribution. There's two challenges here. First, their formalism is based on the VFT equation, right? So they manipulate their distribution by changing the T naught in the VFT equation and saying there's a distribution of T naughts. The second issue is that it still uses fictive temperature. So from a theoretical point of view, it presents some challenges that we're not quite comfortable with. I highly recommend this paper. Wataru did a great job. Alternatively, there's this work from John and I. And the idea behind this space was let's create a dummy landscape or a toy landscape where we create some distribution of basins and barriers that reproduce the viscosity curve at all temperatures. And then use that toy landscape to lower temperatures and see what we predict. So this allows us to predict relaxation without fictive temperature. So it gets around that theoretical issue. The challenge, however, is twofold. First, it is only in qualitative agreement. We do not have the same quantitative accuracy as the MAP model or as Wataru's model. The second issue is that because it's derived from this energy landscape, you actually have to solve the eigenvalues at every single time step. So if you're going to do 1,000,000 time steps, you have to solve the eigenvector, eigenvalue problem 1,000,000 times. So it's computationally intensive. So even though it predicts qualitatively the right behavior, it's still not worth it to be able to do all that computation. So these are the two kind of approaches. The other thing both of these things do is they both try to focus just on structural relaxation. And a key challenge in structural relaxation is that nobody agrees on the best way of measuring it. If you go to the literature, methods for measuring structural relaxation range all the way from DSC methods all the way through dielectric methods and beyond. The standard at Corning or some of these other institutes is to measure literal volume change on a very large scale. And so if you're not melting huge amounts of glass, it's very clean, very high quality, low issue glass. It's very difficult to measure structural relaxation directly like that. So this is a real challenge to be able to quantitatively get data that agrees across many labs, that then also to compare with the literature. The other problem with structural relaxation is the nature of it means that you're subject to all of the thermal history of the system. So how well do they actually report the thermal history, and how much can you really rely on that without knowing it? So it's really a challenge to be able to do this. So I want to thank you. I was shooting for 40 minutes, and I got close. Thank you so much, and I'll take any questions.
Thank you very much for your excellent lecture, Colin. Yeah, we have time for questions. Let me see, 1, 2, 3, starting with Sundaram here. Please.
Great talk, Colin. I always enjoy your talk. The one interesting thing I discovered about the forbidden glasses you were talking about, you probably have seen a lot of world publications showing glass formation region in phase diagrams. So perhaps do you think you can test your forbidden glass, that model, to a binary or a system where historically people have empirically found the formation region, you know? So will that work? Just a quick curiosity question.
Yes, so I think the relaxation model is interesting because it predicts free energy as dependence of temperature. So we wrote a paper on trying to estimate glass forming ability. So theoretically, yes, it can work. In practice, it's not so simple to get right. And also the actual definitions, the metrics that are behind glass forming ability, there's reasonable debate to be had about which ones and how you translate the landscape system into an actual prediction.
Anna?
Yes, excellent talk, really. Appreciate very, very much details on relaxation. Can you talk about a little bit more about the difference between stress relaxation and structural relaxation, and how can you differentiate them experimentally?
I see, yes, I can definitely do that. So let me go back a little bit. Oh. Yes, so let's take an example of this one, which is a work from Corning. Here, the difference is the structural relaxation is the progression towards the equilibrium. So how do people measure that? Usually they take an annealed sample, something that is stress-free, and then change the temperature and watch the decay. And so they're trying to ensure that there's no stress in the system. And here you can see that it is different than stress relaxation. And stress relaxation is the rate at which you relieve stress. So here they were doing it via, I believe, beam bending viscometer. So when you measure the shear viscosity, that is actually related to stress relaxation, not structural relaxation.
Yes, but during stress relaxation, the structure also changes. Yes,
I don't know any more about that. I think that is a really big challenge. Is like how, these descriptions are great, right? And the landscape models are great, but they're either to get the structural details, you spend so much computational time, or to actually get details about the structural changes is really complicated. Edgar has the work combining NMR with MD to look in oxides. And what you see is the distribution of structural units narrowing, right? You see more of the enthalpically favorable unit forming. I don't know if that's universal, but that's definitely the kind of suggestion that's currently out there.
Thank you.
The structure changes a little bit. It will take longer to reach the fully relaxed state, during stress relaxation. It's just shorter. Everything is changing, but it takes, it's faster. Stress relaxation is always faster.
And you can see that
You
here
can see there.
An order of magnitude.
Like an order of magnitude faster. Yeah. But that's interesting because not many people realize this, that the stress relaxation is faster
Yes.
than the structural relaxation. Somebody else had the question here.
Yeah, so going back to the definition of fictive temperature, you said that fictive temperature is the temperature at which you will be at equilibrium if you heat to that temperature instantaneously, right?
Yeah, that's this definition right here.
Okay, so my question is, does that mean that when we use calorimetry techniques to measure TG, and if we want our TG to be as close to fictive temperature as possible, we should use very high heating rates, am I right?
Okay, so let me break that down into two questions. First, what I was trying to point out here is that fictive temperature is a very limiting quantitative idea, but nonetheless, you can describe it this way. I don't know if you're really reproducing the details of the landscape. And if you do define it that way, that's totally fine. There is a method out there by UA from Aalborg called the BIRD method, I believe. And what you do is you integrate two different curves, a heat capacity, and you find the difference and you integrate them to such a temperature that they're equal. So what you're doing is you're trying to match the enthalpy of the liquid to the enthalpy that you had as a glass. And you find the point where they're equal, and that temperature is the fictive temperature. There's a little bit more detail to that, but we can talk more during the break if you like.
Okay, thank you.
I have just a comment about the 100 seconds
Yes.
definition. And well, the key idea, I think, is that the typical relaxation time would be the viscosity over bulk modulus.
Right.
So if you take a viscosity of 10 to the 12 Pascal second, and the typical bulk modulus of 30 gigapascal for an oxide glass,
Right.
it's 33 seconds. But we are engineers, say, well,
Yeah,
33 is 100. 33 is 100. You know, close
Pi
enough.
is 10, 33 is 100.
There, 33 is 100. And that's how this thing came up. However, if you take like an organic glass,
Very different.
the G, the bulk modulus, is only 1 gigapascal or 2 gigapascals. So the actual TG, if you measure in a DSC with a typical heating rate, then the TG will show up at a viscosity of 10 to the 11 Pascal second, not 10 to the 12. So this 10 to the 12 Pascal second, it's a nice approximation for a typical silicate glass, etc. Right. Even for a borate glass with a lot of alkali modifiers, it will not work very well. So it's an approximated,
Of course.
you know,
Right.
idea which works okay for our typical oxide glasses. But just to complement your, you know.
Yeah, no, I totally agree. I think when my students write papers, I try to encourage them to say specifically the definition that they're using throughout the whole paper of the glass transition, so that we can make sure that it's standardized for people who are, you know, especially if you're new to the field, right? You can find, when I teach Intro to Glass, we spend 2 days on glass definitions, and I think I bring, last time I brought 20 of them from 20 different books, and none of them agreed, right?
No.
So it takes a long time to get them cohesive.
Any other question? Okay, good. Thank you so much, Colin, for, again, your excellent lecture. And so we have enough time for a good coffee break now. So please be back right at, let me see, here. Is it 10:15? We should be back. 10:15. But please be back here at 10 past 10. 10 past 10 back here. We have a nice coffee break now. Hã? Ah, aula dele. É sempre assim.
Really differentiate stress relaxation and structural relaxation. Maybe she asked the same, but is that possible? Because I have curve, yes.
You see, if you're not careful, you see a mixture of them.
Right. What I'm talking about. So they have different. I mean, it's different functions, right? Okay, yeah. So, and if I have alpha and beta constants of the structural relaxation, will it help to, or it's not?
You can try. It's best to do them separately and then try to add them.
Okay. About glass transition, one more question, I will go. So, for annealing, right? As I said, usually people anneal glass at glass transition, but DC gives, as I read in some papers, approximately 10 degrees high sometimes. Is it true or not? Some methods giving, I mean, for Qatar glass, for example, is 470 DC can give, right? The glass transition. Yes. I've read in several papers that, for example, dilatometry can give 460 in this case, 10 degrees lower. So, which digit I should trust in this case?
It depends on what definition you use.
I need just real annealing temperatures.
It's best to go lower.
We'll go over, okay. Okay.
It's really hard. Unless the GSC is done the same way by the same people. It's really hard.
So it's just the best option just to see from practical, right? So okay, thank you. Very nice talk. I understand half and something, yes, but I am not thermodynamic guy.
Yeah, no worries. That's all good.
So maybe you can recommend me some book. I mean, I'm reading Mazurin, but maybe also something.
George Shearer has another book that's really
George
Shearer.
George Shearer, okay.
Yeah. Shearer worked in Vassar for a very long time.
So, sorry, just write that. Somewhere.
Minha apresentação aqui. Hey, great talk. Thank you. That's mine. So there's this one.
Okay, thank you.
George Shearer actually dedicated this book, I think, to Mazarin.
Mazurin, okay. Thank you. Yes.
Such a bromance for dedicating your book to your friends. Yeah. One question, Colin. If you had infinite money and only 2 years, what experiment would you do to push the frontiers in this area? Scattering, Newton scattering.
Do you already have this book? You do, I guess so. Você tem esse livro, Daniel? This
Oh, thank you.
is a
Thank you
gift
very
for
much.
the
Thank you very much.
instructors.
I will add to my library here. I think it's. How can I make this work? É esse computador que vai ser usado.
Sim, sim. Sim, esse.
Ah, esse não.
Não, ele tem um. É esse aí. É esse aí. Hã? Só que o laser é terrível. Tem um laser digital.
Laura pediu pra te entregar? E aí, Marcelo? Como é que tá a sua batalha?
Grande!
Grande, Chico, tudo certinho, que bom revê-lo.
Tudo bom? Muito bom. Tamo aí, bicho.
Forte.
Bom vê-lo.
Bom, digo mesmo.
Chegou?
Eu cheguei ontem, mas ontem eu cheguei já no almoço, já tava na fazenda já, eu não pude participar aí.
Não, mas que bom.
Mas cheguei ontem, agora dando aula, não dá pra participar da semana toda, daí eu tenho que fazer uma negociação com a chefia lá.
Eu negocio.
Graças a Deus, aí até tinha procurado no serviço, você chegou.
Eu cheguei eu cheguei, sentei mas daí tudo bem?
Bom, graças a Deus. Como é que tá lá o Paraná?
Então, tá grossa. O operário na Série B já é equipe
falei entre nós, é campeão mundial. Então melhor que o Palmeiras. Tá, né? Já tá melhor que o Corinthians. Já tá melhor que o Corinthians. Não vou nem falar, né, Marcelo? Nem falar, né? Ontem foi pra lá. Chegou aí, eu não ia falar nada, você que tocou no assunto, cara. O Márcio tá se segurando aqui. O final foi outro. Essa conversa podia ser a mesma coisa que já ainda tá. Ou mais.
Vai pegar café? Vai falar pra gente chamar frutos do mar.
Recorta ele uma foto da República, assim, ó. Nunca tem. Nunca. Eu vim pra hoje e amanhã só. Pra hoje e amanhã. Chegou hoje? Não, eu cheguei ontem à noite. Bem à noite mesmo. A gente saiu de lá às 6, 4 e pouco, chegamos aqui às 11 horas. Daí. 450, por aí. Daqui? Sim. Mas eu acho que é por aí. Mas eu acho que até de Ponta Grossa pra cá a estrada é melhor do que daqui pra lá. Mas bem que pra Minas Gerais não precisa de muito pra melhorar a rodovia. Ana que passa um pouco mais pra trás. Já foi. Tudo de bolinho.
Não. Vem as meninas também, por favor. Ainda que você está aqui, Doro. Eu ia falar que eu não tô tomando café.
Ajeitar meu cabelo. Agora vem, André. Vidro existe.
Vidro existe. A Ana também quer a cópia dela.
Primeiro, nesse celular, ó, 1, 2, 3, 4.
Ah, não vou contar. É o número de fotos já. É o número de fotos.
Sorriso,
Vai lá.
Parece não, só os desejos, coisa boa. Coisa boa. Estamos no Brasil, super calor.
Aí.
E aí, Dani, tudo bem?
Tudo certinho, vamos ver.
Marcos, perdi
Não, eu sabia que você vinha só no final de semana.
Mas vou
O Edgar.
Legal. Eu falei um pouquinho, assim, bem rápido.
Vou falar. Legal. Como que tá Ralf, o pessoal lá?
Chegou a ver antes dele ir lá para a Bahia, não sei se você lembra. Ele chegou aí, lá em Ralf, ele conheceu o laboratório.
Mas conversa, depois a gente...
Perfeito.
Eu vou pegar um café.
Cara, eu vou precisar ver. Deixa lá. Institucionalmente, mas eu preciso ver projetos
Okay, is everything working? Yes, 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 please. Rebecca, please bring 2 if you can. Faz um favor para mim. Corre lá e pega umas 3 águas para tarde, porque aqui não tem água. Corre lá. Sim. Não, Ah, ele pegou. Aí sim, obrigado, porque aqui não tem água. Vamos por aqui, ó. Vou chamar os professores, obrigado. Excellent. No, for the next teacher. Thank you so much. I'm so
Down there, there's like 20 students still down
I
there.
know it's impossible to get everybody here back, but I think we have to start.
Presentation will probably be short.
A little short, like 40 minutes. Maybe you can slowly start. You guys slowly start and then you accelerate. Okay, I guess we have to start this session. And again, it's a huge pleasure to host here Professor Rebecca Welch, my co-author in a very nice paper. If you do not cite it, I'm going to cite on my lecture, our joint paper. And she is also a former student of famous Professor John Mauro, and she also loves computer simulation stuff and understanding the vitreous state of matter, right? So Rebecca, thank you very much for.
Thank you, Edgar. All right, hi everybody. So great to be here. There's a couple more students coming in, so I'll talk slow. So today we're going to talk about 2 kind of modern models now available in the literature. They've been available for about 10 years or so. And before we really dive into them, I kind of want to ask the students some questions. All right, so we've heard a lot about different models now. You just heard about different relaxation models, right? We know that there are several viscosity models in the literature, right? You might be working with ionic conductivity models, right? So one question that I want to ask that might seem kind of silly, but it's kind of important. Why do we even need models in the first place? Why do we need models? River, you're making a sintering model. Why did you do that? Did you just wake up one day and be like, hey, I want to make a sintering model just for fun? Oh. hold on. Can you, wait, Pavel, can you introduce yourself?
When I was at university, so I had some space for work. I mean, for example, I can melt 10 or 20 compositions to answer the questions. I mean, how to develop the glass. Usually now I have 1 or 2, maybe 3 steps required. People need to solve, people need from me to solve problems fast. So, and in this case, if you have some modeling tool which can at least predict the right direction to reduce the error, it would be nice.
Very nice. All right. So models help us predict things faster, help us point us in the right direction. Anybody else want to add to that? Why do we need models? River?
We can use models to verify what we know about what's going on in experiments or like the real world, basically. So like if you have a model that works with experiments, you know it's like physically sound, basically.
Okay, very nice. All right. Oh, yes, Edgar?
You know, I guess one of the main features of working with a model is to be able to predict phenomena without having, you know, spending all the time in the lab, which is costly, takes time, sometimes it's dangerous, you know, working with high temperatures or radiation or something. So the prediction ability of models is a key feature, I think.
Yes, I agree. Yes, I agree. All right, awesome. Okay, second question I want to ask, which might be a little bit more challenging. What makes a good model? Oh, a hand? You want to introduce yourself real quick?
I think a good model can be a model that is reproducible and scalable as well.
Yeah, so a model that is reproducible and scalable. What do you mean scalable? Oh, so you can scale it to a larger system? Okay. Anybody else want to add to that? What makes a model good?
Firstly, model should give us the values which it can measure, and that prediction of these values should be more or less the same like we measure it. So it cannot, you cannot measure like viscosity with reality. It's like, for example, 10 to the power of 14, and your model gives you answer like it's 100. It's bad model in that case.
I like that. All right, Kyle?
I think a good model also, a lot of people are talking about how predict and so on, but I think how the model fits with other models and the physical meaning behind that model. So it's not just if it can predict, but if it has a physical meaning behind its predictions.
Right. Is the model physical, right? How is the model derived, right? We have multiple viscosity models. They are all meant to predict relatively the same thing, the viscosity, but they're all derived very differently. Most of them are empirically derived, right? Versus the Maega model for viscosity is physically derived, right? It's derived from the configurational entropy, yeah? So as you kind of see this presentation, I want you to think about this, right? And as you progress throughout your careers, I want you to really evaluate and really criticize the models that you're using in your PhD research and the models that you might see in the literature, right? What makes that model good? Should you just blindly trust that model, right? How was the model derived? Where did it come from, right? These are all really important questions. And I want you to think about these two models as I talk about them. And I want you to think about if these models that I'm about to talk about are good. And then we'll talk about that and discuss those, okay? All right, awesome. Okay, so to begin now, so the challenges with glass design, yes, as we pointed out in industry, right? When, as engineers, our job is to take chemical elements from the periodic table, put them together so that we can create a brand new material, a brand new glass that has desired, tailored properties, right? And our playground is the periodic table, right? The periodic table offers us 10 to the 52nd possible chemistries. This is all calculated by Dr. Zunoda. And so far, only 10 to the 5th have been reported or researched, okay? So there's a lot of new compositions that we can discover, new combinations in which we can put elements together to get new properties, to get better glasses, all right? Now, historically, because of the nature of glasses, right, designing glasses have been with what we call the cook and look method. You guys heard of the cook and look method? I don't know if it's just a US phrase, kind of. Okay, so cook and look, right? So it's just kind of like how it sounds. We, take a base glass composition and maybe we add 10 mole% more of sodium and we add like 5 mole% of potassium just 'cause. And then we make it, we cook it, put it in the furnace, and then we look at it and we measure it. And then we report all of its properties. And then we do it again. Oh, maybe we add 10 more mole% potassium, So really, glass design is extremely challenging, and a lot of it is done empirically, okay? This is not all wrong, right? We've gotten a lot of really great glass products from this method, right? Glass ceramics was a complete accident discovered by Stuckey, right? He put a glass in the furnace malfunctioned, he took the glass out and accidentally dropped it on the floor, and it completely bounced instead of shattering, and that's how we got glass ceramics. So trial and error, or just accidentally finding compositions and new glasses, it totally works, but it's very time-consuming and very expensive. So ultimately, what we want to do with glass design is we want to first determine the composition. Once we do that, the composition tells us what the structure is going to be, right? And the structure completely dictates what are the mechanical properties going to be, right? What is the viscosity going to be? What is the TG? Everything about the glass is all dependent on the structure. And to get the structure, we have to first come up with a composition, okay? So what can we do instead of trial and error or the cook and look method? We can use quantitatively predictive models or methods to help us accelerate this glass design process, right? And these two models I'm talking about today, the first one is the statistical mechanics model of glasses. This is what we can use to predict the glass structure, all right? And once we know the glass structure, then we can also predict the TG, the Young's modulus, the glass hardness, using a model called topological constraint theory. And these models were both developed by Dr. John Morrow, as well as multiple Corning scientists, right? And these models have been used over the years by Corning to help reiterate and make better Gorilla Glass, to also help them design better Corning products or new Corning products, right? And something that's also rather special about these models is that they are universal. They are transferable to theoretically any glass system, right? You just need to use the basic model and then you can apply it to your specific glass family, okay? All right, and if we were kind of to look at where these models fall in terms of how empirical or how physical the model is, we are lying right here, okay? So not entirely empirical, such as machine learning, but also not 100% using fundamental physics for every single iteration, such as molecular dynamics, all right? So this is where we lie. Okay. So the statistical mechanics model of glasses. First, I'm going to show you results, because they're always more exciting before I go into, the derivation and stuff. So these are results in which Bolker et al., which is a really great colleague of ours from Aalborg University, working with, he got his PhD already, but he did his PhD with Morten Smetzger. And this is for the sodium and potassium silicate system. Not super exciting, but what we can see is it's predicting the fraction of Q4 units as we increase the amount of modifier, or sodium or potassium, and then we can also predict when are the Q3 units forming, when are the Q2 units forming, and etc. So the lines are the model predictions, and then the symbols are comparing the model to NMR results, all right? And we see that the model is really great at capturing what we see from NMR, which is awesome, right? We're already connecting with experiments. It's great. Okay. All right, some other predictions in which this model has been used. It was used to predict binary phosphates. So phosphates definitely have a more interesting structure than just binary silicates. But here, we can see that the model does a really great job. Anywhere you see a down arrow, so these are the specific compositions in which the author fit this model to. And based on those fits, they were actually able to fully recover the structure of a binary phosphate system when compared to NMR data, okay? All right, next one, lithium borates. Borates are great because of the borate anomaly, which is awesome and super fun to model because of how strange it is, right? So for the borate anomaly at 0% lithium, we have 100% Q3 units, or B3 units, sorry. And as we slowly add more modifier, we start seeing B4 units form up to a maximum and then decrease. Past that, as we keep adding more modifiers, we then start to get B3 units with MBOs, Q2 and Q1. All right, so what's great about this model is we've seen that it can actually capture the borate anomaly as well. And it was compared to NMR results from Feller et al. From Coe College from 1982. Okay, so how does this model work? All right, so this model works by assuming that the probability of forming a structural unit. So what I mean by that, what is the probability of forming a Q4 unit or a Q3 unit, right? And the probability of forming that is analogous to the probability of drawing marbles from a pool. This is a very simplified definition. I'm going to expand it, so this is not 100% accurate yet. But just as an example, if we have a sodium silicate glass of 20 mole percent sodium, 80 mole percent silica, we're going to now treat it as marbles. Cool. All right, so that means for our modifiers, right, so it's Na2O, that means for 20 mole percent, there's actually 4 sodium marbles or atoms. All right, so now they are in a pool, and then next to that is a pool of our network formers. So our network former is silica, and we are already assuming that all the silica are 4 coordinated with 4 bridging oxygens, okay? So that is our initial way of thinking about this. And when we look at our first sodium here, we're going to draw a silica Q4 unit from this pool, and this sodium is going to interact with it. What's going to happen to the silica Q4 unit? Yes, yeah. It turns into a Q3. Yes, very simple, right? So this sodium, it draws a Q4, and that is going to result in now a Q3. All right? So then that Q3 unit gets put back into our pool of network formers, and now we have 7 Q4 units, and now we have 1 Q3 unit. Okay? So now we're going to do it again with the next sodium. Okay? So for our next sodium, right, it can either draw a Q4 unit again, or it can pick up that Q3 unit that we just made, right? And what's going to be the result then? If it picks up that Q4 unit, that's going to result in another Q3, right? If it picks up that Q3 unit, what's it going to create? Q2. Very nice. Yes, absolutely. Yes. And those will now get updated and put back into a pool. And so the other thing that we need to understand is what is the probability of forming that Q2 unit versus that Q3 unit, all right? And that probability is given by this expression here. So this is now our StatMech expression, and this is what we're going to talk about. So expanding on the definition now, so it's more accurate, okay? So how the model works assumes that the probability of a modifier interacting with a network former depends on entropic and enthalpic factors, all right? So entropic, it just refers to how many Q3 units are there in the pool, or how many Q4 units are there available for that sodium to interact with, right? Enthalpic means how energetically favorable would it be to form that Q2 unit. If you have a pool of Q4 units, right, we generally know that the sodium wants to go to those Q4 units and create a Q3 unit, right? And that can be expressed in terms of how energetically favorable it is. So it is energetically favorable to form that. So if we break this equation down, this omega here is the entropic contribution, and it's just simply the number of network-forming species available. And we're going to talk about it more, don't worry. And then here, this is our enthalpy. This is telling us how energetically favorable is it to form that structural unit. Okay, that's the basics. So now on to the best part, the derivation, right? As physicists, we love to see derivations. This is the good stuff, okay? So, and why are we talking about this? Because it's important to know where our models come from, right? How are they derived? Are they physical? All right, so the first thing we have to do to derive this model, since it is based on statistical mechanics, right? So we consider the Boltzmann distribution, which describes the probability of a system to be in a given state as a function of temperature and energy here. So the probability of being in a specific state, all right, we're going to apply it to glasses in a bit, but this is just the basic structure here, is equal to 1 over the partition function times this Boltzmann weighting factor. Now, before we expand on this, who can tell me what is the purpose of a partition function? Why do we need to include a partition function? Where does it come from? Ooh. I know the Alfred kids know. Yeah? Okay, maybe other people? Okay, specifically, what about the distribution, though? What does it do to the distribution by having a partition function? Normalizes it. Yeah, exactly. Exactly. Seems kind of like a silly question, but actually that was the question that my thermodynamics professor asked me at my qualifying exam. So good thing I knew that, but good thing you know it too. All right. Oh, I'm sorry. Do you want to say it again? Thank you, Edgar.
So the partition function normalizes the distribution.
Normalizes the distribution so that all probabilities equal to 100%, right? All right, so the Boltzmann weighting factor, which is this other part, is a very common expression that we see all the time, everywhere. Diffusion, we saw it in the relaxation models, and what it's really just saying is if you were to plot the probability as a function of energy, so here, this E, I don't know what this Greek epsilon, yeah. So this is referring to an energy barrier, right? So if you were to plot that energy as a function of probability, it would decrease as a negative exponential. So at this end, at 0 energy, all it means is that there is a 100% probability that that event will occur, right? And as we increase the energy, we see an exponential decay of that probability, all right? Make sense? Okay. Cool. So now we're going to expand this. All we're doing is expanding the partition function here. So now this is our entire expression. So the probability of being in a certain state depends on the energy and the temperature of that state, divided by the partition function, where you're summing up all the total number of states. Okay, now we have that basic formulation. Now we have to apply it to glasses. So how do we take this and apply it to predicting the glass structure? All right, so the first thing that we do is now this probability I, instead of a specific state, it's saying what is the probability of forming a specific structural unit, okay? So that probability is here, and now what we can do is we can replace this epsilon with the free energy associated with forming that structural unit. So what is the equation for Gibbs free energy then? Yeah? Yes, G is equal to H minus Ts. Thank you. All right, cool. So what we're going to do, we're going to replace it. We're going to rewrite it a little bit, but H, enthalpy, minus entropy times the temperature. So now we've replaced that, and now we're going to introduce the statistical entropy of the system, where entropy is equal to K log omega, and omega is referring to the specific number of microstates that represent a given macro state. All right, so we're going to replace that entropy term with all of this in both here and here. Cool. Now we get this. So now enthalpy minus the entropy term here times temperature. And now we're slowly referring to this entropic contribution that we saw before. So let's simplify. All right, first thing we can do, distribute negative. Okay, we get that. We can simplify again. All right, so what's a really easy thing we can simplify right now? Yeah, Lauren? The exponential? Yep, and the natural log here, so we can just take that out. Cool, awesome. Now we get our omega out front, and if we simplify the partition function as 1 over z, we're starting to now get our actual stat-mech equation here. One other thing that we have to do is this temperature is not necessarily referring to a specific state from the initial definition of the Boltzmann probability, but now when we apply it to glasses, we're saying that TF, that the temperature is actually the fictive temperature of the glass, the fictive temperature of that specific glass. Sorry, let me say that again. The structure in which the glass is frozen in is the fictive temperature, and what we do normally is we assume that the fictive temperature is just equal to the glass transition temperature of the glass. Okay? Cool. All right. Okay, so now we have our expression. And the very last thing that we have to talk about is what is this omega and how are we applying it to predicting the glass structure. So the omega, right, we saw where it came from, but all it is telling us is it's just the number, the initial fraction of network forming species, right? So the initial fraction of our Q4 units in that beginning example, minus the number of species that have already been modified, okay? So this is just saying how many silica units can we work with? That's it. All right. So now if we were to do that structural prediction again, more accurately, what we could do is first we can predict the fraction of Q4 units. So here this is a calcium silicate glass at 0% calcium. We have 100% Q4, which is why we have that dot here. So all 7 of these are Q4 units. So the specific fraction of Q4 units that we would expect is given by this equation here. So fraction of Q4 units at the current draw, right? So what sodium marble are we at, or calcium marble are we at in this case, is equal to the fraction of Q4 units at the previous draw, which we haven't done a draw yet, so it's still 7, minus the probability of forming that Q4 unit. And that probability is exactly what we just derived, okay? So the only thing that we need to really know is, well, fictive temperature, right, which we assume is the TG. And then more importantly, though, we need to know what this enthalpy parameter is, okay? So for this case, we will fit that the enthalpy parameter of a Q4 unit forming is 0, all right? So we're already saying that the energy to form a Q4 unit is 0. And as we said before, with the Boltzmann weighting factor, that means 100%, we have 100% probability of having a Q4 unit. All right, as we slowly start to form Q3 units then, the fraction of Q3 units, right, is given by the fraction of Q3 units from the previous draw minus the probability of forming a Q3 unit plus the probability of forming a Q4 unit. And so the probability of forming a Q3 unit has its own enthalpy parameter, right? Our Q4 unit, we already said, was 0. And then now we are slowly predicting what is the Q speciation of this glass, all right? So now we have 2 Q3 units based on this. The rest are Q4. And we also then need to know what is the enthalpy of forming a Q2 unit as well as a Q1 unit, okay?
Rebecca,
Yeah.
Can I ask you, how did you get these enthalpies? It's not sure, the enthalpies.
That's a great question. I will talk about that, yes. I'm glad you're thinking about it. How do you get the enthalpies? That's a really good question, yes. All right, so if we keep doing that, then we get our structural prediction of all of our Q species. All right? Oh, here's the answer, Edgar. To obtain our enthalpy values, okay, we have to fit them. There we go, yeah.
Sorry.
I knew I was getting to it soon. I don't know when. Yeah. All right, so we have to fit our enthalpy values. We have to fit it to enough data to where we are able to extrapolate, say, our predictions to a very large compositional range. So for Bodker's work, in some of his papers, I think he said that he fit to 12 data points, okay, and then was able to capture the entire rest of the compositional range, okay? All right. So here is where you can also use MD if you don't have NMR results, but that also introduces limitations, right? All right. So another limitation of this, then, is that theoretically, these enthalpy values, they should be physically meaningful, right? They're specifically referring to what is the enthalpy needed to form a specific structural unit, okay? But what we've seen from the literature is that these enthalpy values, they're not always transferable. Sometimes you need like a smudge factor. Sometimes you need like to shift the enthalpy values to make it work. And what I mean by transferable, let me clarify. So when you do, say, our calcium silicate system, that calcium interacting with a Q4 unit or a Q3 unit that has a specific enthalpy, right? So if you were to, say, take that, but then look at, say, a ternary system, such as maybe a calcium aluminosilicate, that calcium and silicate interaction, that should still have the same enthalpy value that we saw in the binary system, okay? But what I'm saying is that that is not always true. You don't always get the same exact value. So the question is it actually transferable? If it's not, then is it really a physical parameter? All right, the other assumption that we need to really consider is that the structure is represented by the fictive temperature, which we assume is the structure that we'll see at the glass transition temperature. All right? And then a question that I want to leave to the audience for the students is, what other assumption or assumptions do you think this model has that might be problematic? I'll give you a hint. It has to refer to how we initially think about the structure and how we're forming the structure. All right? Okay. So, oh, you have a guess already? Very nice. Do you want to give us your name real quick? Sorry, I forgot it.
So I'm Adam from Warsaw, and I think that maybe there is an underlying assumption that each unit is separate, where in fact they may form some sort of clusters or they can interact with each other. And maybe, for example, a unit, for example, Q2 may be more probable when in neighborhood of other Q2 units. And this enthalpy may not be constant throughout the structure.
Okay. Very cool. So you're saying that possibly there's an interaction between, say, a Q2 unit and another Q2 unit? Okay, maybe. In terms of how this model is developed, we're only looking at, per se, what is happening with each modifier draw. But that's very interesting. All right. If anybody else has any idea. Oh, Lauren? Yeah?
Is it to do with the assumption we made for the entropy value that we used? And is that, oh, okay, never mind. I thought that was
The omega is just the number of species that we're working with. Ah, I see. I think we'll see kind of what the answer is when I talk about the next model as well. Okay, so question then, is this model a good model? Thoughts? Who thinks yes? No one? One person? Who thinks no? One person? Yeah, two people-ish? Three? Okay. All right. Do you want to elaborate, Marcio?
Thank you. This question is tricky, right? For an explanation, yes. A good explanation, yes.
Okay. Wait, is it a good model or a bad model? Oh, a good model. Oh, okay, sorry. Oh, good model. Oh, cool. Very nice. All right. I thought you said a bad model. Sorry. All right. Well, maybe something to think about. All right. If you want to use this model, Volker, he did an amazing job and put together a free open source code for you on GitHub. And currently, it's developed for these systems here. What would be awesome, though, is if we got more students to apply this model to see how it works, to test it, right? Can we test how good is this model, right? By applying it to other systems, yeah? So that is available for you. Okay, moving on. Topological constraint theory. All right, once again, we're going back to our problem of glass design, right? We just talked about the StatMech model in which it can predict the structure. But now, if we know the structure, then we can use this model to predict the glass properties. Okay. And again, I'm going to show some prediction results, some model results. So here, this was first published by Morrow, Gupta, and Laux. And here is the prediction for a sodium borate system and lithium borate system. And you can see they predicted the glass transition temperature. And when they compared it to experimental results, we saw a really great prediction, yeah? And same thing for lithium borates. All right, here we can predict the glass fragility as well. So here are the model predictions for binary borates. Not super great, but in other systems, we can really predict the fragility a lot better. All right, this was work done by Smedsker, in which he used TCT to predict a ternary system of sodium-calcium borates. And here he predicted what the TG was along this ternary, as well as what the fragility was. Okay? These are really cool graphs. All right. We can also predict the glass hardness. So here, what was the, oh, this was for an alkali germanate system that I looked at. And we looked at, oh wait, no, this is not mine. I have my hardness predictions later. But anyways, I don't remember what this one was. Sodium something, probably borates. And we can predict what the hardness will be. And then here, we can predict what the Young's modulus will be compared to MD data for this example. Okay, I'm going to go through this one a lot faster than StatMech. All right, so for the TCT model, where did it come from? It came from work by Phillips and Thorpe, as well as Gupta and Al Cooper, all really, really famous glass scientists. And really what this entire model is saying is that we can treat the glass as a network of constraints, and we can use that to predict these properties. Okay. So this was initially inspired by civil engineering. I took these directly from Dr. Morrow's slides. And so the explanation is that, right, is that Phillips and Thorpe initially looked at how these structures are made. And if you specifically look at, say, the Eiffel Tower, you can see that these pillars, or the how the tower is constructed, it has constraints, right? So we have constraints here that keep these areas in place and keeps them rigid, right? So this is how we get a rigid body. This is how we get a stable, strong structure, okay? When we apply it to glasses, what we're saying is that if we look at the number of constraints, and if they're equal to the number of degrees of freedom, which I'll explain in a bit, then we get an optimal glass. So what we're really saying is if we have enough rigid constraints, then we get a rigid backbone. We're forming a rigid backbone of our glass network. All right, so what does that really all mean? Okay, so if we think about, say, just an atom, just floating, right? Each atom can move in 3 directions, X, Y, and Z direction, right? But as soon as we, say, add some bonds to it, those bonds introduce constraints now. So now that silicon atom, right, it can no longer be as free. it has decreased the degrees of freedom because it's bonded to these other elements now that are keeping it constrained, keeping it rigid, right? This is why we have a strong glass network, right? All right. So if we kind of expand on this, the mechanical and thermal processes now, or properties, sorry, can be predicted if we know how many rigid bond constraints exist, right, in the glass composition. Okay, so the first thing that we have to do to use this model then is we have to determine what is the total number of bond constraints in our glass network. And that is actually really simple. We have to know first, though, what is the coordination number of each network-forming species. All right, so for every network-forming species then, we have to sum up all the different types of constraints. And there's two constraints. There's a linear constraint, so here, germanium to the selenium, right? That is a linear constraint, just like when we saw with the silica, this silicon and this oxygen, that is a linear constraint. And then we also have to consider the angular constraints around it, right? So these are the different angular constraints. And we can do it really simply with a paper by Wilkinson et al. In which he simplified all the TCT down into these really nice equations that we can just simply fill out to figure out the number of linear and angular constraints. All right, so the number of linear angular constraints, they depend on, first, we need to know the mole fraction of our network-forming species really easily if we have a binary silica system. All right, so 60 mole % silica, this would just be 0.6. And then the only other parameter that we have to know is what is the coordination number of our network former. All right, for silicon, that's 4, yeah? So we just plug that information in, and now we get our constraints. So then how do we use this information to get, say, the glass transition temperature? All right, so with that was developed by Morrow and Gupta, and they showed that the glass transition temperature is proportional to the configurational entropy of the system. So down here, wherever there's a R, this is just referring to a reference composition. So we're predicting the glass transition temperature using one reference composition, using the TG of one reference composition for our system of interest. And that is equal to the configurational entropy, which is dependent on the TG as well as the composition. Okay, so we can make this a little bit easier to work with by using the work from Namas, in which he showed that the configurational entropy is equal to the atomic degrees of freedom. Now this is really nice because we know how to calculate the atomic degrees of freedom because we know that they are related to the number of constraints, which we just figured out how to calculate. All right, so to predict the TG, what we really need to ultimately do is know the number of total constraints of our system. So D is the dimensionality of our system. We're in 3 dimensions, so that's always going to be 3, unless maybe you want to do like, I don't know, a surface or something, that'd be kind of cool. And so then this N here, right, this is just summing up all of our constraints and summing up all of our network-forming species. But we have to introduce one more parameter, and that is the temperature dependence of each constraint, okay? And I'll explain that very briefly in a bit. Okay, so what is this onset parameter? So this is a continuous function that is saying, is this constraint going to be active at a certain temperature, all right? And generally what we do is we just treat it as a 0 or a 1, okay? If it's a 0, then that constraint, we don't have to worry about it, right? Whole thing goes to 0. All right, if it's 1, then it means that it's active. All right, so what does that kind of mean? Hopefully this will make a little bit more sense. Okay, so if we were to do kind of an example system here of, say, a calcium luminosilicate, what kind of constraints exist? That's what we first have to determine. Well, we have to know that there are a bunch of linear constraints. So here we're considering the silicon-oxygen linear constraint, alumina. Here, maybe you want to consider that calcium and alumina is contributing to the rigidity of the network. And then we have our angular constraints here. Next, we have to say, okay, are these constraints active at our specific temperature of interest? And we do that simply with, is it a 0 or a 1, all right? If it's a 1, then we're going to use it in our model. If it's a 0, then we're going to say, we don't need to worry about it, okay? Remember, this is a summation of all of them, okay? So we have to sum up all of these.
Rebecca,
Yeah.
excuse me. How do you know if the constraint is active or inactive?
Yep, I'm just going to explain that too.
Ah,
Really great
come on.
question.
I
No,
will
that's
stop
awesome.
asking questions.
I'm really glad that you're thinking about these. All right. Okay. After we do that, we calculate all of our active constraints. All right, so here's an example then of some results. So this is a TG prediction here. So this is our TCT model compared to experiments along a compositional range. And what's really cool about the TCT model is we're calculating all these constraints. We can actually see which ones contribute to our property of interest. So here, this is our TG prediction up here, these dotted lines, right? It just looks strange because the y-axis is now very different. But what it's saying is that the TG, or yeah, the glass transition of this specific system is mostly comprised of linear alumina constraints, and this is linear silicon constraints. Sorry, it's really dark. All right? So we're saying that all the other constraints are not active, okay? So the last slide was kind of a lie, but this is the actual result. Again, I'll come back to that, how you determine that. All right, moving along a lot quicker. I'm definitely not going to go over these, okay? So what we can do, we can predict the glass hardness, the Young's modulus, as well as the fragility. In order to do that, we have to relate all of these properties back to the number of constraints. So what would be really cool for students, maybe in their research, is to try to find other properties that we could maybe predict using TCT. In order to do that, you'd have to develop your own model. And for that, you have to relate that property back to the number of constraints so that we can use this to predict it, all right? And for all of these are fitting parameters, okay? So we have to keep that in mind as well. Okay, another example before I answer Edgar's question. So this was TG predictions of alkali germinate systems. So this was to try to understand the germinate anomaly a little bit better. Here's our TG, and here all we saw was that the beta is, oh gosh, I don't remember what the beta was. This was specifically referring to an angular constraint of germania. This was from my paper, but I don't remember because it was so long ago. And then here we saw a prediction of the fragility, and we saw which constraints are contributing to this prediction. Okay, here again, here's our elastic modulus. This is for our ternary calcium aluminosilicate system, and we can see all of the constraints now and how they contribute to our modulus. Same thing here. This is for our glass hardness. All right? Okay, now to the limitations. All right. So the first one is kind of a big one. We have to already know, right, what is behaving as a network former or as a network modifier. All right? That can be kind of a tricky assumption, right? It's kind of controversial. What is a network former? What is a network modifier? So this is kind of what I was thinking in terms of what is the other limitation of the statistical mechanics model as well, right? If you remember the StatMech model, that is saying we have to assume that, say, our calcium is behaving as a modifier, right? So that when it draws, say, a silica unit, it's forming a Q3. It's forming a non-bridging oxygen. That's a pretty big assumption for elements that we don't really know, right? We don't really always know whether a certain element is behaving as a modifier. All right. And then to determine whether the constraint is active or inactive, it's generally fit to experimental data. All right, so what do I mean by that? Going back to my examples, all right? So this is from our calcium aluminosilicate system. These were all the constraints that we had to think about. Not all of them are active, obviously, for each property, but these are all the ones we had to look. So for the TG model, right, we tested, okay, is this linear MBO and bridging oxygen constraint active? Does it give us a decent prediction, right? If not, then we're going to say it's not active, all right? So for the linear silica and alumina constraints, right, when they're activated, when they're considered, what is that going to do to our model, yeah? And if it does not, if it gives us a super wonky prediction, then what we're saying is that it probably is not active, okay? So from our results, from all of these different constraints, the only thing that we saw that gave us the best fit was that the linear alumina constraint and the linear silicon constraint were active, okay? So this is where that constraint, whether it's active or not at that certain temperature, comes into play. Okay. All right. So I want you to think, is this a good model? We're not going to talk about it, but let's think about it, okay? So there's definitely a lot of limitations to every model, and what I want to really leave you with is a very famous quote. Lots of us, we know this quote, and we love it a lot. And the quote is from Dr. George Box from Princeton University, and it just says that all models are wrong, but some can be useful to us. Yeah? All right, thank you.
Thank you so much, Rebecca. We still have exactly 5 minutes for questions. Marcio? No?
Thank you, Rebecca. Nice talk. Following Edgar's question about the molecular dynamics simulation, you said that you obtained the enthalpy from simulation, right? The question is if that values that Bodker got from simulations can match somehow to enthalpy formation or something like that from experimental data. Here.
Oh, sorry, I found it. Yeah, that's a really great question. So no, those enthalpy values, they're not directly, say, like the same enthalpy of formation that you would find in maybe a chemistry textbook or something, right? They're just specific values for that specific system. So in my opinion, I would say they're empirical and not necessarily physical.
Okay, thank you. So our models are wrong, but you show a lot of models that works, right? Okay, thank you.
Yes, yes.
Oh, sure. Yeah.
Okay, so thank you for your presentation. And I have one small question. When you can calculate the constraint number in one of your page, you compare your gas computation with the reference computations. How to define and how to know that's the
that is literally just one single data point. So say you were looking at the lithium silicate system. So your reference composition is you would need one data point of one composition in that system. So you would fit it or compare it to, say, maybe one glass that is 10 mole% lithium and 90 mole% silica, if you have that TG information available. And then as long as you have that one reference data, then you can do the rest of the calculation. So that's kind of really nice. You don't have to necessarily fit to multiple data points. It's just one. Yeah.
That means the reference class computation can be found by themselves. They can use
so you would just do one TG measurement, and that's all it would take to get an entire TG of an entire compositional range.
Okay, I see. Thank you. Thank you. Some more?
Hi, Rebecca. Thanks. Quick question. And now what? What do we do with topological constraint theory? Where is it going? Where is it headed? What's the cutting edge? And is it really going to be useful in the future? Even if we can predict things with some AI models and things like that. Where is all of this headed now?
Well, that's a great question. I think that's completely up to the students and up to the people that need to use these models, right? To design glasses for specific properties, right? So say you need a glass that has a specific fragility. Now we have some basic information. If you know some things about the structure, then you can maybe predict the fragility and then use that to help you, right? These are not like, oh, you only need this model and that's all you need for the rest of your life, right? These are models that can help guide you in the right direction. Yeah. So in terms of what next, I don't know.
Okay, thanks.
Thank you.
Thank you very much, Rebecca. This is a very nice slide, a poster actually, that was produced for an International Year of Glass, showing all number of applications for glasses in art, culture, healthcare, etc. It was produced in Japan and translated here. But I'll give you a fresh sample to take to Alfred.
Yes, thank you so much. This would be great.
Few samples. And also we have several here, so if the students want to get some, you can get some here. It's really nice. I'll save some to the professors before they disappear. But there's still a lot here of these posters. And talking about posters, Ricardo now has very strong tape, so you can stick your posters. Thank you. You can stick your posters because this afternoon already did. But this afternoon we have a poster session. Anyway, move on to still computer simulations on a different topic. Daniel Casar, our emeritus Lamavian, who is now a professor in Campinas. He is an expert, became an expert on machine learning techniques. So Daniel, thank you for... Você tem um? Você não tem? I gave enough too. Ah, you guys want one. Okay. There are still several there you can get, but rush, there's not enough to everybody. See, so let's take Rebecca again.
Hello, everybody. So good morning. Thank you, Edgar, for the introduction. I'm going to talk a little bit about the use of artificial intelligence and machine learning and these computational strategies to discover new glasses and predict properties, right? I'm painfully aware that I stand before you in lunch, so I will try to be brief. I have more slides than minutes, so I will skip some slides. I'll try to be really brief, starting with an introduction. This is just a plot, just to get started, right? Number of papers within the material science and engineering field with two different keywords, artificial intelligence and machine learning. And as you can see, starting around 2016 or 17, started to peak, started the interest in the community, and it's going up. So it's, I guess, a very hot topic right now. I like to start by defining things. Have you ever thought what is artificial intelligence? Because it's a buzzword, right? We hear it all the time. there are actually 4 branches of artificial intelligence. If you want your computer to think as a human, you need to go to cognitive sciences. It's really hard. We're not there yet. It's really hard to understand our brain, but it's not our field, right? It's not for us. If you want the computer to think rationally, then you go study logic. This is a very nice field, but it's a way to make computers do artificial intelligence. If you want computers to act as a human, then you can use these large language models. Everyone has spoken with ChatGPT or DeepSeek. They act as a human. They are just probabilistic machines, right? But they kind of trick you that they are human, right? This is also a topic of the famous Turing test. And finally, if you want your computer to act rationally, then you need to build a rational agent, and I will show you that. Let's define machine learning. So this is machine learning in a nutshell, right? You have a magic box, you have information that, you have some information, you put this information into a magic box, and your magic box spits out the information that you want. Okay, I could call this a function. It's just a function, but calling it a magic box, it's more impactful, I guess. And you will create this magic box using data, right? We have these procedures, these algorithms that will look into your data and will create this magic box for you. And you have this magic box inside you, right? Let's see. What I'm showing you is some syntactic data, and I have 2 descriptors of these materials. You can think these descriptors can be, I don't know, the amount of silica, it can be the temperature that you produce at your material, I don't know. I don't care. They are just 2 descriptors of your materials, right? And we have the squares, they are glassy materials. We have the circles, they are crystalline materials. And I'm going to make that triangle over there. Who here thinks that will be a glass? Okay, that's your magic box, I'm not judging. Who thinks that will be a crystal? Right, this is your internal magic box thinking, right? I don't know what it will be, but you acted rationally. Oh, I have some data around this triangle. They are all crystalline materials, so probably your triangle will be a crystalline material, and this is what our magic box will do. I want to define 2 other terms, inverse design and forward modeling. So inverse design is really good for industry. It's when you have a set of properties, a set of constraints that you must meet for your product, right? And then you will use some tools that I will call inverse design to find some candidate materials that fits your requirements, right? This is inverse design. And Rebecca already told us about cook and look. This was, and I guess is still the most famous technique to develop new materials. It's quite time consuming, it depends on luck, but it's what we have. There are other tools, I will discuss a little bit about this. But one thing we know, we cannot use physics to solve inverse design problem. We just can't. And every time I say this, some people make weird faces. If you know how to solve this with physics, please let me know. Please publish. I really, really want to know that. We also have forward modeling. This is just what Rebecca calls a model. I'm calling forward modeling. You have a set of descriptors of your material, and you will put this into your model, and it will spit out some property or characteristic of your materials, right? And what can we do with models? Huh? Well, this was the last talk. What can we do with models? If you have good models, you can do inverse design with these models. So forward modeling is interesting because we can solve some industry problems that is finding materials to meet certain criteria. And I mean, we have lots of models. We saw many models today. We saw MD, we saw constraint theory, and we can use DFT, we can use Monte Carlo techniques, and we can also use these data-driven techniques, including machine learning, that I'm going to talk today. It will be the focus of the talk. Let's talk a little bit about glass, and Rebecca already laid all the slides for me, so it made my work easier. So, as Rebecca said, we can make glasses using all the periodic table practically. And the space of glasses that we can make is huge, right? Because we are not limited to silicate or oxide glasses. We can have metallic, organic, inorganic glasses. Okay, so the whole periodic table is at our disposal. Glasses do not have strictly stoichiometric rules as crystals do, so we can continuously change the composition. If we change the composition, we change the distribution of chemical bonds, the chemical bond types, and so on and so on. We end up continuously changing the properties by continuously changing the composition, and this is great, I guess. We already saw this. This is the Materials 101 flow chart, right? Let's see what happens with glasses. So glasses, most of the commercial glasses are produced by melt and quenching. I guess more than 90%. I love sol gel, I love vapor deposition, but let's be true, most of commercial glasses are made by the same process, melt and quenching. We are talking about commodity glasses, we are talking about specialized glasses, same process. Okay? What happens is that the structure of the glass, we saw talking about this, it will remember the liquid, right? Because you're frozen the liquid. When you're cooling down, you're frozen the liquid. So your frozen structure will remember the liquid that it once was, right? What I want to say is that if you oversimplify a lot, you can say that the properties of glasses are highly dependent on the composition. This is, of course, this is a simplification. We saw it today. We have a relaxation. We have so many things to think. But on average, the properties are highly dependent on the composition. And this is a huge opportunity. And people have used this kind of approximation. And that's what I'm going to show you with a brief literature review, right? So this is the first paper that uses, as far as I know, that uses machine learning techniques in the field of glass by Dreyfus and Dreyfus. They used a neural network to predict the liquidus temperature of some oxide glasses and got a very nice result. And you can say, oh, but liquid temperature is a crystalline property, right? But you know, you need to melt and quench your glass, so I will say this is an honorary glass property, okay? We also have this work by Brouwer and co-authors. They also use a neural network, and they predicted the chemical durability. In the last slide, I forgot to mention, they used about hundreds of data points, right? Hundreds. In this paper, they used 31 data points on oxide glasses to train this neural network, to find these correlations, to induce this magic box, right? Right now, I don't think you could publish this paper right now, because with only 30 data points, you cannot train a neural network. But I mean, that was 2007. So it's a good paper. It's a good paper because it invited the community to think about this, right? We need to understand the situation that we were. Now let's go to 2016. It's a huge jump. This is a paper by John Mauro and co-authors. Again, they used neural networks, the type of machine learning algorithm, to predict the liquidus temperature, again, very important. With hundreds of data points, got a nice result. This, 2018, is a paper by Anup Krishnan and his group, and he tested many different algorithms. I told you about neural networks, but we have other types of algorithms, of strategies to induce your magic box, and they tested many of these strategies to predict the dissolution rate of silicate glasses with, again, hundreds of data points, right? One thing interesting, they informed their model with physics. If we have time, I will tell you a little bit about this, but this is important. We can inform these magic boxes using our knowledge of physics, right? Very nice paper. And then, 2018 again, this is a paper by Professor Zanotto, André de Carvalho, he's a professor here at the State University, and myself. And we pushed a little bit this boundary, right? Instead of hundreds of compositions of data points, we studied 10,000 of data points. What's the expectation? The expectation is that your magic box, when you are inducing it, if you show lots of data points, perhaps you will have a better magic box. Just the idea. But another thing that we have in this paper is that we were able to sample a very significant space, both considering our target property, that was TG, right? Glass transition, and considering the compositional space. We studied glasses made by 1, 2, 3, up to 21 different chemical elements, right? And that's great because, remember, we can make glasses using all the periodic table, and perhaps we can change the properties in an interesting way. So this is a paper that I think it's the first to use like 10,000 data points. I couldn't find any other in the glass field, right? And after this, there was a boom, right? We will stay all day talking about the papers. I'm just writing here the milestones, right? So right in the next year, we had the viscosity model, a Young modulus model, then density, shear modulus, reduced TG, and so on. At some point, we started thinking about chalcogenide glasses instead of just oxide glasses. So this is a very rich set of papers, of publications, of advancings. And you can read all these papers by Anup Krishnan, Adama Tandya, Edgar Zanotto, myself, Mathieu Bauchy, John Mauro, Bingui Deng, Ashutosh Goel, Morten Smetzger, Jing Chengdu, Charles Lelos. There are so many people working on this, right? I don't have time to dwell on all of these papers, just to show you the main picture. Now, in 2023, there was a new model, right? This is the model I'm going to discuss with you today, give you a zoom on this model. That's GlassNet, okay? That's the model that I worked on, I developed, and this is a neural network, a deep neural network. What it means to be a deep neural network, this is a buzzword, right? It's just a neural network with more than 2 layers of neurons, of artificial neurons, okay? It's just a buzzword for this kind of stuff. This model receives as input the composition of the glass. Remember, this is highly, the properties are highly dependent on the composition, and it spits out 85 predictions for 85 different properties, okay? So 85 predictions. And I'm going to talk a little bit about this model. It was built using the SciGlass database. It's free and open source. I will show you in a moment how you can use this database yourself. There was minimal chemical filtering, so I was not restricted to oxide glasses. So we have oxide, chalcogenide, halogenide, everything that is inside SciGlass. After the query, we end up with about 280,000 data points. Think about an Excel table with 280 rows, right? This is not good because we have duplicated data, right? Many people have measured, for example, the TG of silica. So we will have one entry for each of these measurements, and this is not good. We need to have only one entry for each composition to train our magic box. So there's a deduplication step where we collapse all this information. Perhaps if there's more than one number, we can apply some median, some mean value, whatever. We collapse this all, and we end up with about 220,000 data points. That's a lot of data points to train the neural network. So this is the pipeline. We have the data with the chemical composition. It goes through a thing called the featurizer. What's a featurizer? It's a thing that uses this composition to compute other descriptors, using physical chemical information, using other information. There's this featurizer. I will skip the slides, but if you have questions, I can, perhaps in the questions part, I can talk a little bit more. Then all of these features go into a neural network, and it spits out your predictions, 85 different properties, okay? Just to repeat, it's not limited to oxide glasses. What's the challenge? It's finding the architecture of this neural network. Because there are so many moving parts, there are so many dials that you want to select, how many neurons, how many layers, what's the activation function, and so on. And so there's so many things that you need to consider to build your neural network. And this is, I think, the hard part. And I mean, I can tell more about this to you in the questions part, but I guess in the interest of time, I will just skip. But this was done. This is reported in the paper if you're curious. And this is what we get. A model that gets composition and spits out your predictions of properties. It was hard to see in the previous slide, but just so you know, we can predict viscosity, we can predict optical properties, the electrical, mechanical, optical, thermal. There are many types of properties, many things that we can predict. It's on the paper. I will skip the kangaroo slide. Perhaps I can show you another time. One question is, this neural network is a multitask neural network. So it's one neural network that predicts 85 different things. And this is a different approach than what was done in the literature. It was one neural network to predict only one thing. Now this is one to predict many. Was this change of paradigm beneficial somehow? It's yes and no at the same time. For some properties, it was beneficial. What properties? Properties measured, the same property measured at different conditions. You can think about viscosity, for instance. You can measure the viscosity at different temperatures, but is it still viscosity? Physically, is it still the same thing? For these kind of properties, it was good. Why? Because as you learn to predict one viscosity, this information can help you to predict viscosity at another temperature, right? For some properties, it was statistically equal if you had a multitask neural network or a single task neural network statistically equal. And for some properties, it was better to have a single task neural network. What I mean is that a specialized magic box that predicts only one property. For which cases we have this? For cases with lots of data points, properties with lots of data points that were not measured at different conditions. Perhaps hardness. It's only micro hardness that you have available inside glass. You don't have hardness measured in different conditions, different loads. It was not beneficial. But there's a solution. We can build a hybrid magic box. So you use your magic box to predict the properties that the multitask predicted better, and for the other properties, you use the single task model. It's an easy solution, right? This is GlassNet. It does this for you. After you have your magic box, you can kind of open this magic box looking for insights, right? There are tools to try to find insights inside these complicated models. Sharp values is one of those tools. I will not get into the details. The math behind it is a little bit complicated. But the thing is, after you have your model and you compute these sharp values, I can tell you that from the data, if you want to increase young modulus in your glass, you will have a good chance of increasing young modulus if you increase the magnesium amount, or if you decrease the phosphorus amount, or if you increase the alumina amount. What I'm trying to tell you is that this kind of information, if you want to design new materials, may be useful. You know where you can fine-tune your composition, and we can get these insights from the trained model.
Daniel, just a question. Could you go back one slide?
Of course.
Yeah. It's a little surprising that calcium increases the elastic modules, right?
Yeah.
Just a little
But I mean,
surprising.
it's a correlation. This is very important. These are all correlations. It's not causation, right? We know from statistics. So perhaps it's something that we need to investigate. I don't know. But it's the correlation that the model learned. Yeah? But interesting commenting. Thank you. And we can build, using these models, we can build on top of these models. So these are viscosity points predicted by the model. They are not experimental. And we can use, we can fit our favorite viscosity equation. This is my Maiga equation, but you can fit whatever equation you want in these data points, and then you have a model. You have a model that you can interpret and perhaps extract some physical meaning. So we can build on top of these models. Now let's talk about inverse design. Remember, to do inverse design, we need to have these models, and I will show this to you right now. When you want to do inverse design, you have the set of properties, and you want to find some candidates. And I just want to repeat, because this is important, physics will not help us here. In the inverse design part. In the forward modeling, yes. Inverse design, no. What's one solution? The cook and look is one solution. Rebecca told us that. What's another solution to do inverse design? Random search. What's random search? You define your search space, the compositional space, and you sample your candidates. You go to the lab, you melt your glass, you measure the properties. Is it good? Great. Your job, finish it. is not good, you sample another one. Remember, we can make glasses with the whole periodic table, right? So the sample space is a bit huge, right? So random search is not good. But we have grid search. We all learned grid search. What's grid search? Grid search is that instead of picking randomly all the compositions, you will sample all the compositions to check if you find your answer. Can we sample all the glasses? Can we make them? We can't. We can't. It's more than the number of atoms in the universe if you want to do them all. You can't. You can't do all the glasses. So there must be something in between random sampling and making it all. And there is. And I'm going to show you today that we can solve this problem using genetic algorithms. It's a type of optimization algorithm based on evolution theory and natural selection from Darwin, right? And I'm not saying that this is the only solution. Of course, it's not. But it's a solution that I'm going to show you. I guess I have a few minutes. I want to do a genetic algorithm with you live, just to show you the main concepts, right? First thing you need to do, you need to define your genetic space, quote unquote, right? What's your genetic space? How you will define your material? Here I'm defining my material, my glass, as a vector of 4 numbers, 4 genes, if I may. Each gene will be representing the molar fraction of some compound. So we have silica, we have lithium, sodium, alumina. If you want to write sodium disilicate, it would be that vector down there. This is how you write this composition, right? So the first step is you define your space, and then you need to generate your initial population. It's random, right? It's a random process. So you just sample some numbers. This is your initial population. First step, you will do natural selection. You will select the best materials that you created in the first step. How? Using your predictive model. Using your model. So let's say we want to increase the hardness. We want to find a glass with a very high value of hardness. We will pass these values into a model. It will spit out the hardness for us, and the probability of selecting an individual to the next generation will be proportional to the hardness. So the higher the hardness, the higher the probability of the individual being selected. That's how you use these predictive models in this algorithm. After selection, we can do crossover. We can mix and match the genetic information of the glasses in the hopes that perhaps one individual had a very good gene for hardness, and another have another good gene for hardness, and in the mixture, one of the children will be better than the parents in the genetic way, thinking about hardness, right? So this is an example where we are mixing the genetic information of 2 parents, and we can do mutation. It's similar as genetics, right? Some genes will be randomly selected to change the value. It's the only opportunity that you have to bring new information to the table, right? Because selection and crossover can only mix and match what you already have. With mutation, you can bring new information. In this case, we have a post-processing. This is not necessary because we want the composition to sum to 1, right? So this is the basics of genetic algorithms. But so what? The idea, the expectation actually, is that after each generation, you will be a tiny little bit closer to a possible solution. Tiny little bit. So you do this many times. If there is a solution, there's no way to know that there is a solution. If there is a solution, the expectation is that after many generations of doing this, you will get to the solution. And this is what we did in this paper. We wanted to find new glasses for application in smartphone lenses. They must have a lower value of the G because when you are molding these glasses, you cannot go to higher temperatures because it damages the mold, right? So it needs to have a value of Tg below 500 C and a higher refractive index, higher than 1.5 because it will be lenses, right? It will be used as lenses. We did this, so we used neural networks to do the forward modeling. We have models for Tg, for refractive index. We used genetic algorithms, the similar way that I showed you. And we got some candidates, and 2 of these candidates we melted and checked if they met the conditions, right? One thing to note is look at the complexity of these glasses it would take a lot of time to find these glasses by trial and error or by pure luck, right? Let's check what's happening. So these are the predicted values for TG and for refractive index, the model prediction, right? We made the glasses in the lab and we got these values. And it's not perfect. I know it's not perfect. I tell my students, if you want perfection, go away from machine learning. It's not perfection. But we got it, right? We wanted TG below 500C and refractive index above 1.7. We got it. Let's see the authors. Professor Zanotto, Dr. Giseli, and myself. We are not experts in, in optical glasses, right? Professor Zanotto is an expert in many things, but it's not the main field of Professor Zanotto, right? And we were able to develop glasses in a field that we were not experts, right? And we actually tried only true glasses, right? We're not hiding anything from you. We tried true and we got true good results. I think this shows the power of this kind of techniques.
Daniel, just a short comment. There was another restriction here. We wanted niobium. That's important to mention.
Sure, forgot to mention that. We wanted niobium and we got that. Okay. So let's talk a little bit. I think I have some time. I have 15 minutes, right? Okay, let's talk about data scrapping. These data-driven models, they require data, and I know, thank you, Captain Obvious, of course, but I need to say that, right? And inverse design requires good models. We have a definition of a good model, right? Rebecca gave that to us. SciGlass database, which is free and open source, has data only until 2019. And if you say, no, I'm willing to pay, I will pay, I have money, you can buy Interglad. That has data only until 2019. So we have 5+ years of glass data that's not available in a convenient way for us to build these models. And there's lots of good data there. We're missing out. So we would like to go through this literature and get this data, and so we can use to build these magic boxes, right? And before we move forward, I just want to tell you that I've never worked with data scrapping. This is, I received an email from Professor Zanotto. Some of you were in ICG and asked Professor Zanotto, oh, can Daniel talk a little bit about data scrapping? Okay, I will, but I never worked with that, so I'm being frank with you. And I was reading this paper by Anoop, and actually creating an automated way to scrape data is still one of the 21 challenges of the 21st century. So we are talking about the frontier here. I don't have a solution. If you want to go to lunch, I don't have a solution. I will tell you what are the problems here. What are the sources of data, right? We have books, we have papers, we have patents, we have handbooks, right? These are all written material. What are the challenges? Text is unstructured data. It's really hard to get data from text, and I will give you some examples. We have quote-unquote chaotic tables. So everyone likes some kind of type of table, and I will show you some examples. It's really, really hard to get data from table in an automatic way, automated way, because there are so many types of tables, right? We need to account for that. We have format variety. Your paper may be in PDF. You can also download XML. You can download HTML. There are many formats. If you build the best pipeline for PDF, it won't work for another data structure, right? So that's a problem. That's a challenge. If your book or patent or whatever, it's somewhat old, you don't have a true digital format. So someone had to scan the document and pass through an algorithm to identify the characters. This is prone to errors, right? And can you measure that? I don't know. We have terminology differences and ambiguity. Perhaps in one paper, TG is defined as 100 seconds. In another, is defined as the viscosity that's 10 to the 12 Pascal second. Perhaps you have different units. Some people like Pascal, some people like gigapascal or another crazy unit. You know, this is not easy to do this in a controlled way. And on top of that, if we are talking about papers, you need to ask permission, right? You cannot go and download all the papers. You need to go to the publishers, go to the editors, and you need to pay, and you need to download and process. It's not easy, and you need to ask for permission. So it's very, very hard to automate data scrapping. I really want to convince you that. But let's try. Let's see this easy example. I have this phrase here. Silica was synthesized at 1800 C for 2 hours. Using this black magic called regex, we can, in 3 lines of code, get the temperature that's written in this text. So we have this tool called regex. It's a text processing tool. And after you program it, you can easily get some information. In this case, with these 3 lines, we get the variable temperature now holds the information 100 degree C. What we will do with this information, I don't know. But you already captured that, right? You need to write more lines of code to capture more information. Perhaps the word silica, it's a hot word. You need to capture that, synthesize it. 2 hours, that's 2 words. Perhaps you need some strategy to capture more than 1 word. Okay, this is an easy example. Let's see another. We all like to write things like this, right? We don't like to write our papers directly, right? We love these fancy phrases. Let's see this phrase. DSC of sample AIM18 revealed the values of 950 C and 1300 C for TG and T-liquids, respectively. Oh, that's difficult, right? What's the composition of AIM18? Perhaps it's in a text in another place. Perhaps it's in a table. Perhaps it's in the supplementary material. That's crazy, right? How can we get this composition? Then we get the temperature, right? We run the code that I showed you. We get the temperature, 13,000 degrees C. We get this temperature. This is closer to TG, right? We want to check proximity. This is not TG. This is the liquids. So if you just check proximity, the simple algorithm, you will miss. You will get the information, but the wrong information. So it's a real challenge. Possible solution. Perhaps we can add some large language model to interpret the paper and check if it can find the correlations. Perhaps it can find what composition is AIM18 and the respectively word, connect the dots and check what's TG, what's the liquids, right? I'll talk a little bit about this in a few slides. Now let's see the papers that we have. Let's see where we got. Most of them are by Professor Anup Krishnan, right? He's in Germany right now, I guess. Yep. In this paper, Anup and his group, they collected many papers. I hope this was not me. He collected many papers, and he could classify the papers by their topic, right? Only by looking into the abstract. So by reading the abstract, oh, I know this is a crystallization paper, this is a mechanical properties paper, this is a thermal property paper, and this is interesting because it's hard to read all the papers, so it's good to read the papers that you want, right? If you want to collect crystallization data, you don't need to bother with mechanical properties data, okay? Very nice paper. Let's see another one. Another from Anup's group. This is called NER, Named Entity Recognition. So we can run an algorithm to check the words and try to extract some meaning from these words. Let's see the second phrase over there. Glass ceramics is in green. That means it's a descriptor. I don't know what material it is. I need to check it out, but I know it's a glass ceramic. This is describing my material. Let's see the next word, sintered. Let's see the color-coded. It's a synthesis method. I still don't know the material. I know it's a glass ceramics. I know it was obtained by sintering method, right? So this is very interesting for us because we're starting to connect the things. We're starting to name things as they are. Then we try to extract this information. And this is free, by the way. This is Matt Seibert. You can get that on that link. It's free and open source. You can run it yourself and classify your texts, right? So next step we have. Remember that I mentioned Remember that I mentioned chaotic tables. This is another paper by Anup's group, and they checked all the types of tables that we have. They identified it, I guess, 9 or 10 types of table. Gosh, there are so many types of table. And for each type of table, you need to have a specific algorithm to extract this information. And they published this paper and developed this tool called Discomat. It's also free and open source. So we are solving the problem piece by piece, right? So tables are somewhat solved. And I want to use this opportunity to talk a little bit about some of my colleagues, my Brazilian colleagues. They do not work with glasses, but I just want to bring attention to their work. This is Thiago Bottari, and he published this paper where he, in the co-authors, they could read the paper and extract some synthesis recipes. So let's see that composition in red right there. The barium, cobalt, iron, and stuff like that. They could extract, okay, this is the product. I need some precursors. These are the methods that I need, and the conditions of these methods. They could extract this from the literature. So how do you make this kind of materials? They got that. Perhaps we can read this paper and fine-tune this for glasses, right? Another colleague of mine, Amaury de Paula, he developed a software, also free, called Arix, that could read the PDF files, extract information on experimental design for producing carbon functional materials. And then he understood, oh, what's the best route? What's the best byproduct of industry that we can use to improve, I don't know, energy efficiency? I don't know. It's not my area of expertise. But another Brazilian researcher working on this field, right? Not glasses, but perhaps there are some interesting tools over there. And finally, not finally, but closing somewhat this part, this is a student of ours, André Caetano, and he's working with data scrapping. He's an undergrad, he's not for glasses, but I somewhat interviewed him and asked, oh, tell me a little bit about your work and stuff like that. And this is a phrase that he told me. For data scrapping, you will need to use these large language models. That is, DeepSeek, ChatGPT, Llama, Gemini, I don't know. You need to use these models. Why? I showed you. It's really difficult to connect information, and these models are great at that. And you can do this for free using this software called Olama. It's free. So the software can download the model, you can run on your, on your machine is a bit strong, but on a cluster, and then you can use these tools. You don't need to pay. You need to pay for the papers, but not for these models, right? So this is interesting. He's working at the frontier, and it's something that we need to keep an eye on, right? And how the glass community can work together, right? So I stayed a week on Professor Andrea laboratory at BAM, and she and their group, they are developing this very nice platform called SciGlass Next. She probably told you yesterday. Well, that's the link. And as far as I know, the idea is to join the community so we can work together and have a platform to share data, to share all things glass related, right? So this is quite interesting. I know it's a difficult task, but we need to start somewhere. And they are at the front line doing this, and I just want to call your attention to this. I guess so. Yeah. 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 So there's only one way so we can really advance our field fast, is if we work together. It's the only way, I guess, in my opinion, right? I don't have time to talk about this. Sorry about that. Closing words. I mentioned that you can use SciGlass data, and you can also use GlassNet. It's free and open source. This is a software that I've been developing for some time. It's called GlassPy. If you know Python, go check it out. It's free. You can get your SciGlass data. You can easily use the models and stuff like that. Just to finish, these are my closing words. Just to remind you that we can make, quote unquote, infinite many glasses, right? And this is a huge task. But these data-driven tools, these artificial intelligence tools, are helping us to navigate intelligently in this huge catalog. And just a bit of myself, right? To tell you, the young researchers, right? Choosing an open science approach was one of the best choices of my professional life, right? Because I showed you GlassPy and it's free. It could not be free. I could try to sell it, but it's free, it's open source, people are using. And it was, at least for me, it was the best choice of my professional life. And I just want to pass this information to you. Okay, I want to thank all my collaborators, Brazilian researchers, students, and international collaborators. And I want to thank the financial support of CERTEV, Materials Informatics INCT, CNPq and FAPESP, my organization, and thank you for your patience. We can go to lunch now.
Very good. Thank you. Thank you, Daniel. Some questions to Daniel? Well, let me organize myself. There are lots of questions now. Okay. 1, 2, 3, 4, 5. Wow, I lost my count already. So let's start.
So I just wanted to ask, because you said that there are many problems with data scrapping, and at the same time you mentioned that you used 55,000 glass compositions that were available for the database. So how were that data collected?
Oh, yes, yes.
A lot of data.
By humans. SciGlass was built by, I talked with Priven. Priven is one of the creators of SciGlass, and they use it to pay grad students to collect the data. So it was humanly collected.
Yeah, they were reading papers. This is Professor Oleg Mazurin in St. Petersburg many, many years ago. They were reading papers and collecting manually. So they produced the handbook of glass that I have, you know. And later on, it became SciGlass, you know, by Alex Priven, who now works for Corning in Korea, but was manually. Unbelievable. But it stopped in 2019 or so, right?
Yeah, 2019.
2019. So there is need to upgrade, you know, to add many more data there. Okay, Leo. Okay, I'll give you a chance now.
Congratulations, Daniel. Fantastic work. You talk about the difficulties about getting the data, but how about the data quality? If you talk about classic compositions, it's okay, bad data will get just mixed up and erased. But when it comes to exotic compositions, and you showed 2 examples of exotic compositions, you need good data of these exotic compositions, and eventually bad data on that will give you some problems. So how do you filter that?
Yes. I didn't. Okay, that's great. Thank you for your question. No, I mean, there are strategies. There are strategies. For instance, the duplication strategy. If you apply the median instead of the mean when you have more than one value, that's more robust against bad data. So it's one strategy to sample out data points that are bad if you have more than one measurement. It's not always that you have more than one measurement. Another expectation, right? The way that you train these models, you can change how it will fit to the data. And you have some control on that. And you can tell the model, look, try to pass through all the points, but if you see something weird, don't bother. So this is a way to not, if the thing is too good to be true, you don't go there. So there are strategies. Some other strategies that Professor Zanotto is working, he told me, perhaps you can detect outliers in the data. There are strategies to detect outliers, and you can do this stuff. But I mean, for this work, it was only removing the duplicates.
I'd like to know how you deal with with the problem of overfitting for the data.
Yeah, that was the slide about how to train a neural network, right? There are many strategies that you can do, but we don't have time here, perhaps during the coffee. There are many strategies that you can do to try to minimize overfitting. And perhaps more important than that is to identify overfitting, if you have. Because minimize is one thing, but you need to identify. And cross-validation is your best choice to identify, right?
Thank you. Great talk, and it's an exciting topic. Do you have one of your descriptors, errors and error limits in measurement? So, as you know, besides data quality, every measurement has several sources of errors, and you also have compounding error. So I haven't seen, and maybe that's one of the descriptors, but could you tell me something about it?
Yeah, that's a great question. I mean, everything has some uncertainty associated, and we cannot avoid that. For these models, this was not considered, but I mean, if you go to statistics and if you think about modeling the distribution of your descriptors, of your data, I'm certain you can put this into your model. I'm certain because I've never worked with this, but I mean, the statistical people, they figured this out. But that's difficult because how do you know the distribution of errors, say for silica? It may be, how do you do that? I don't know. Yeah. I just want to, of course, but of course. Yeah. Of course, never.
And there is this is very important because there is another very important source of error that we met in the early days when, take silica glass, pure silica glass, right? Pure silica glass, the TG, the reported TG of pure silica glass goes from 900 to 1100. It's not incorrect measurements. It's just the degree of impurities that silica glass has, like water, for instance. You know, the measurements are okay, but it's an intrinsic problem with certain properties, especially like transport-like properties, ionic conductivity, diffusion, relaxation, crystallization. They are sensitive to minor impurities. Other properties like, you know, density, thermal expansion coefficient, a little bit of less or more, some impurity, it doesn't make any effect. But transport properties are very sensitive. Take our preferred material, lithium disilicate. Take the crystallization rates of lithium disilicate. They vary by 2 orders of magnitude. Not because the measurements were wrong, but because of impurities or colors.
If the crucible material isn't stated, then tellurium oxide can be a gram more dense because the aluminum got into it.
Anyway, yeah, you're right. We still face many problems, but things, you know, keep moving. We are.
How is it, Rebecca? All models are wrong, but some are useful.
Some
if
are
it's useful, then you can use it. If it's not, throw it away.
Professor, thank you for your presentation. I would like to know, considering glass ceramics with heavy metal oxide that have limited available data, how can you predict the properties of these materials? And also, in the models that you have built, how did you ensure that the model is not memorizing the data, but truly finding relationships?
So the first question, if you don't have lots of data points, you can still use data-driven techniques, but you need to understand that you just can't do better than a certain threshold, right? You will be limited. Your model will be limited somehow in its accuracy, in its prediction. But have said that, if you are developing new materials, you can use these models to guide your development in a way called active learning. This is the key word, right? It goes like this. You want to increase hardness and decrease, I don't know, Young's models. I don't know why. Then you build your model with your field data points, and then the next material you will make, you produce, it will be one that, at the same time, tries to meet your requirement. And if it meets your requirement, you're good to go. You finished your work, right? You can go to have a party, right? If it does not, it's the best data point to improve your model as you feed it back. So it's a feedback loop where you're always choosing a great candidate that at the same time will be good when it's fed back in the process, right? Active learning is the key word for you.
Yeah, but for glass ceramics, he was asking about glass ceramics.
Yeah, but I mean, you can do this for glass ceramics. You cannot use my model, but you can do this for glass ceramics if you have the data points. Yeah, it's not overfitted, right? Cross-validation. The key word is cross-validation. I will take other questions, but I can tell you what is cross-validation, but using this keyword, you will find how.
Let me go to that side a little bit.
Thank you for your excellent talk, Daniel. At the moment, all the input data is experimental. Can't you use physical modeling to generate the structure and then feedback or we are not yet there yet with good modeling?
Yeah, I cannot say if we are there yet. This is not my specialty, but yes, if you have data and you somehow have confidence, at least some threshold of confidence in your data, you can use it. So you can use MD, like Professor Hino told us today. You can use MD to get data and then do the same procedure.
Then the second question, is there, if I have to choose, let's say I have a good physical model that can predict a property,
yes,
and I have machine learning. Why should I use machine learning instead of MD, for example?
If you have a good physical model, and it's really good, as defined by Rebecca, I would go with the physical model, because you can explain, you can convince your peers that you're using a good model. If you don't, then you have machine learning.
Or perhaps in the coming back from properties to composition, ML is the only tool or more efficient tool to achieve this. As you explained before, I mean, I want a glass with certain properties, and then I need to search for a composition. Then ML is better than that.
What I want to say is that these machine learning algorithms, they are so good at finding patterns, but so good at finding patterns that it's, how can I say, it will be very difficult for a human to find all these patterns in these complex systems, right? I'm not saying it's impossible, but, but it's at some level of connecting the information that perhaps we will never reach. So if you have very complex data, it will be really hard to make a good empirical model. Not impossible, but hard. And perhaps this is where machine learning can help us in these scenarios. But if you have very well-controlled data, like we saw the constraint theory, what was the name again? Topological constraint theory, very nice model. The insights are really great, right? But at some point, it may break down, or you need to study other compositions. This is something, the work go on. You need to account for that.
Okay, thank you.
Okay. That's it.
Hi, Daniel. So the objective of SciGlass Next is actually to correct some imprecisions of the data that is available in SciGlass, and also to bring in new data, as you said, right? So the idea, the expectation is that the whole glass community will contribute to this database. But of course, I get back to the question of data quality here, it's a follow-up. It is also expected that the community will help to do the curation of the data. So, you know, if Edgar identifies that there's some absurd data there, he should report this so it can be corrected. So if we all do this, then it makes a lot of sense to have a database. My question to you is, how are we going to do this? Do you have ideas how artificial intelligence could help us in the curation of the data so that before actually inputting the data, we already have a pre-selection of what's good and what's bad data?
Yes, as I said, there are algorithms to identify outliers. So perhaps with these algorithms, you can show to the scientist, oh, be careful with this data. Perhaps there's something here. Not actually labeling as incorrect, but just take care. Another thing that you can do is perhaps, if you have a good model, and your model is predicting a property that's way too far from the data you have, perhaps you can raise a red flag, right? That there may be something here, or the model is wrong or the data is wrong. Someone needs to check, and it's a step for creation, right? Who is going to check? We need to make the glass, we need to melt and measure. So on top of my head, in 2 minutes, this is what I can think of.
What we are doing at the moment, it's doing a machine learning training, and then some data points that are like 5 standard deviations above the expected curve. Then you have to read the paper and take a look. Sometimes, one of my students found a glass with a refractive index of 50, which was great, right? Another one was a negative refractive index. It would be a very nice Nature paper. But, you are right. We have to collectively to find out outliers and report these outliers.
Thank you so much. Great talk, Danielle. Thank you. I was wondering, your talk really focused on connecting composition to properties, right? For engineering, totally awesome, right? But I was wondering if you could comment on the application of machine learning for more fundamental science. Where do you see the opportunity for machine learning in uncovering fundamentals of glass science?
Well, that's a great question. For MD, like Professor Reno told today, perhaps it can help us find potentials.
Yes.
And I'm not an expert, but can I say that we can try to interpret these potentials to find clues, or perhaps use, if it's a good potential, we can use to learn something? I guess this is one way. Another way that I can think right now is there is this thing called symbolic regression. You guys know Kepler? Kepler, when he proposed the planetary motion equations, he used very good data from an Italian called Tycho Brahe. And with good data, he could produce those equations that we know, right? The Kepler laws. There is a way to automate Kepler. We have automatic Kepler in the computer. It's called symbolic regression. If you have good data and you have a good intuition on what do you expect to be the empirical formula of your physical phenomena, symbolic regression can help. Physicists are using a lot this technique. The glass community, I think it's a little bit shy right now, as far as I know. But this is the key word. And I mean, I'm under pressure here. I will leave you with these two answers.
I think now we have to call it a session, an excellent session, I should say. Thank you very much again, Danielle. And please be back here at, say, 1:10, because we have these online talks, and a nice researcher from Turkey will be giving this talk it'll be 10 p.m. in Turkey or so. And then the Japanese guy, Satoshi, it'll be 6 in the morning, so we don't want to be late. Have to be right on time for the afternoon. So please be back at 13:10 at the maximum, even before that, if you can. Huh?
Because originally mine is scheduled at...
No, first your talk, and then they'll be talking at 4 p.m. No, the first talk is your talk. 13. Is 13:45? Oh no, I'm sorry. It's 13:45. No, I'm sorry, not 30. I was thinking about 13:15. It's 13:45, so 13:40. Please be back by 13:40. I'm sorry. Thank you. You'll be here.